Something happened in a laboratory in Geneva that should not have happened. The equipment was functioning perfectly. The researchers were experienced. The conditions were controlled down to the most minute detail. And yet the result, when it came back, was impossible. Not surprising, not unexpected, not merely strange, impossible. Contradictory to everything the team had spent years learning. Everything their instruments were calibrated to confirm. Everything the laws of physics had reliably promised would occur. And the researchers did what careful scientists do. They checked the equipment again, they reviewed the calculations, they ran the experiment a second time, and then a third, and every single time, they got the same impossible result. That should have been the end of it, a strange footnote in a research journal, a mystery for future minds to unravel. But it wasn't the end, because something very similar had already happened in a completely different laboratory, in a completely different country, in a completely different field of science. And it would happen again, and again, and again, until the word impossible started to feel like something other than a final answer. It started to feel like a recurring signal, a pattern, a knock on the door of the universe that no one has yet been brave enough to open. And if this is the kind of mystery that keeps pulling you deeper, subscribe and continue with us into Beyond the Universe, because some discoveries do not resolve reality, they unravel it. Before you can understand why any of this matters, you need to understand what science actually promises you. Because science is not just a collection of facts. It is not a list of discoveries nailed to a wall. Science is a framework of expectation, a deeply confident architecture of cause and effect, built over centuries, verified by millions of experiments, and trusted by every engineer, doctor, navigator, and astronaut who has ever used it to get something right. When you drop a stone, it falls. When you heat water, it boils. When you split an atom in a specific way, it releases a specific and predictable amount of energy. These things happen the same way every single time in every country on every continent, regardless of who is watching. That is the silent contract at the heart of all science. The universe is consistent. It follows rules, and those rules are universal, meaning they do not take days off, they do not have exceptions, and they absolutely do not produce results that contradict themselves. The laws of physics are not suggestions. They are the deepest description of how reality actually behaves. They are the reason bridges do not collapse, medicines work, and satellites orbit with precision. They are the reason we trust the physical world at all, and they are the reason that what scientists keep seeing should not, by any honest reckoning, be happening. You have to appreciate just how much confidence this framework carries before you can feel the full weight of what happens when it breaks. Consider how a physicist thinks about the world. When they walk into a laboratory and design an experiment, they are not guessing. They are applying a model of reality that has been tested, challenged, confirmed, refined, and extended across more than 400 years of rigorous human effort. Newton explained the movement of planets and apples with the same handful of equations. Maxwell unified electricity and magnetism into a single coherent theory. Einstein showed that space and time are not separate, and that mass and energy are two faces of the same coin. These were not lucky guesses. They were precise mathematical descriptions that predicted things no one had ever seen, and were then confirmed, exactly as predicted by independent observers around the world. Science has earned its confidence. The model works. And that is exactly why, when the model fails, not once, not in one place, not in one experiment, but repeatedly, systematically, across entirely separate fields and entirely separate minds, what you are left with is not just a puzzle. You are left with something that feels, slowly and uncomfortably, like a crack running through the floor of reality itself. The first time you hear about one of these anomalies, your mind reaches for the most comfortable explanation available: human error. You think, someone made a mistake. Perhaps the instruments were poorly calibrated, perhaps the data was misread, perhaps the statistical analysis was flawed, or the sample size was too small, or the experimental conditions were subtly contaminated by a factor no one noticed at the time. These are reasonable thoughts. These are exactly the thoughts that good scientists have when they encounter a result that surprises them, because the history of science is full of moments where a surprising result turned out to be a mundane error. The thermostat was off, the cable connection was loose, the formula had a typo. And so the scientific process has built-in defenses against false alarms: peer review, replication, independent verification, statistical thresholds so high that the probability of a false positive approaches near zero before anyone publishes a claim. Science is designed to be skeptical of itself. It is designed to catch its own mistakes. It is designed to filter out the noise and leave only the signal. And yet, The signal keeps coming through, not despite the filters, but through them, past the peer review, past the replication, past the independent verification. The impossible result keeps surviving every attempt to kill it. And that, more than anything else, is what changes the feeling in the room. Let us start with light. Not because it is the most dramatic example, none, it isn't, not yet, but because it is the one that started the unraveling in the first place, and because it established a template that you will begin to recognize as this story continues. In the 1800s, physicists understood light as a wave. This was well established. Light waves travel through space much the way sound waves travel through air, oscillating, spreading, interfering with each other in patterns that are perfectly consistent with wave behavior. You can demonstrate this with a double-slit experiment, which was first performed by Thomas Young in 1801. You fire light at a barrier with two narrow slits in it. The light passes through both slits simultaneously, because it is a wave, and the waves from each slit interfere with each other on the other side, creating a pattern of bright and dark bands on a screen. This is called an interference pattern, and it is exactly what you would expect if light were a wave. Nothing unusual, nothing alarming. The universe is behaving exactly as it should. Now close one of the slits. Block it off completely. The light can only pass through one slit now. There is no second wave to interfere with, and so logically, what you should see on the screen is a single bright stripe, the light spreading slightly as it passes through the open slit, but with no interference pattern, because there is nothing to interfere with. This is what the math predicts. This is what common sense dictates. This is what the physics absolutely demands. And for about a century, nobody doubted it. Then in the early 20th century, scientists began to perform this same experiment with something different. Not a beam of light, but individual particles, single electrons, fired one at a time, one particle, one slit open, one screen waiting to record the impact. You fire the first electron, it hits the screen, fine. You fire the second electron, it hits the screen, fine. You fire 1,000 electrons one by one, each separated from the next by enough time that there is no possibility of them interacting with each other. And when you look at the pattern they have made on the screen, when you look at where 1,000 individual particles landed, each traveling alone through a single open slit, you see an interference pattern, the same bands of light and dark that appear when a wave passes through two slits simultaneously, produced by individual particles one at a time, with only one slit available. There is nothing for them to interfere with, and yet there is interference. And this is not a mistake. This is not a calibration error. This is one of the most replicated results in the history of experimental science. The physicists who discovered this were not casual observers. These were some of the most rigorous, methodical, mathematically sophisticated minds of the 20th century. People like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, names that carry enormous weight in the history of science because they were not dreamers or mystics. They were calculators. They were builders of precise, testable, predictive theories. And what they found when they dug into this impossible result was that the math actually worked, but only if you accepted something about reality that has no parallel in ordinary human experience. Each particle, they concluded, does not travel as a single definite object. Instead, it travels as a wave of probability, a smeared-out description of all the places it might be, all the paths it might take, all the outcomes that might occur. This wave of probability passes through both slits simultaneously, even when only one slit is open, because the probability of the particle taking any given path is still influenced by the structure of the entire barrier. The particle knows about the closed slit. It responds to the configuration of the experiment even when that configuration should have no effect on a single localized object. This is not a metaphor. This is not a philosophical interpretation layered on top of the data. This is the literal description of what the mathematics says, confirmed by every experiment that has ever tested it. The particle responds to the whole experimental setup, including the parts it does not go through. And when you ask the obvious question, but how does it know? Quantum mechanics gives you an answer that is almost worse than no answer at all. It does not know. Knowledge requires a knower. What happens here is more fundamental than knowledge. It is woven into the fabric of what the particle is. But perhaps you are thinking, this is quantum mechanics. This is already the strange realm where we know the rules are different. Perhaps this is not so shocking. We have known for a century that quantum particles behave oddly, and you would be right that quantum strangeness is expected at that scale. But here's the first thing you need to notice about this story. The strangeness did not stay at the quantum scale. It did not politely confine itself to the domain of subatomic particles where it had been discovered. It began to creep upward, into larger and larger objects, into more and more macroscopic situations, until it started appearing in places where it absolutely should not have been, because the quantum world and the classical world are supposed to be separate. You are supposed to live in the classical world where things have definite positions, definite velocities, definite states. The quantum world is supposed to be a different regime, a microscopic domain that averages out into the solid, predictable, sensible universe you experience every day. That boundary, the transition from quantum weirdness to classical normality, is one of the most important assumed features of physical reality, and it is precisely that boundary that scientists keep finding is not where they expected it to be, or, in some experiments, does not seem to exist at all. In 1999, a team at the University of Vienna led by Anton Zeilinger performed a double-slit experiment, not with electrons, not with photons, but with Buckminster fullerene molecules, carbon-60 molecules. Each one is a cage of 60 carbon atoms bonded together in a sphere, a structure so large that in the world of atomic physics, it is practically a boulder. These are molecules large enough to have a temperature, large enough to absorb and emit radiation, large enough to interact with their environment in dozens of complex ways. They are not point particles. They are not simple systems. They are complex, multi-atom structures that exist right on the edge between the quantum and classical worlds. And when the Vienna team fired these molecules, one at a time, at a barrier with 2 slits, they produced an interference pattern, not a faint, questionable signal buried in noise, a clear, unmistakable interference pattern, reproduced across tens of thousands of particle counts, exactly as you would expect from a quantum wave. These were essentially tiny soccer balls of carbon traveling as probability waves. These were macroscopic objects, by the standards of quantum physics, behaving as if they were not localized, definite, classical particles at all, as if the boundary between quantum and classical had moved or blurred, or perhaps had never been quite as solid as everyone assumed. And then the same team pushed further. They did not stop at carbon-60. They kept increasing the size of the molecules they used. Carbon-70, then fluorinated fullerene derivatives, then increasingly large organic molecules. And each time, as long as they could isolate the molecules sufficiently from environmental interaction, the interference pattern persisted. By 2019, researchers had demonstrated quantum interference with molecules containing nearly 2,000 atoms, molecules so complex that they have been described as resembling small proteins, entities that begin to approach the scale of biological systems. The experiment keeps working. The result keeps appearing. The boundary between quantum and classical keeps failing to assert itself where the textbooks say it should. And every single time a new record is set, every single time a larger, more complex, more classical-looking object produces a quantum interference pattern, the same unsettling question reasserts itself with greater force. How large does an object have to be before the quantum world lets go of it? And what if the answer is larger than we have yet tested? What if the quantum world never actually lets go? You might want to pause here and let that land for a moment, because what this sequence of experiments suggests, not wildly, not speculatively, but through careful, replicated, peer-reviewed experimental data, is that the quantum strangeness you might have filed away as a property of tiny things might actually be a property of all things, that the apparent solidity and definiteness of the world around you might not be a fundamental feature of reality, but rather a kind of emergent illusion, a statistical average produced by the fact that large objects interact with so many environmental particles so rapidly that their quantum nature is effectively hidden from view, not destroyed. The word for this process is decoherence, and it is the leading explanation for why we do not see quantum effects in everyday life. But here's the troubling part of that explanation. Decoherence is a process, not a wall. It is a gradual suppression of quantum behavior, not an elimination of it. And if it is a process, if it is something that happens to varying degrees depending on how well isolated an object is, then quantum behavior is not confined to a special microscopic domain. It is a baseline property of reality that our macroscopic world happens to suppress under normal conditions. Strip away the suppression, isolate the object, cool it down, shield it from the environment, and the quantum nature of even large, complex objects begins to show through, like a signal through static, like a pattern underneath the noise. Now step away from quantum mechanics entirely. Step away from the microscopic world of particles and waves and probability functions. Step back to the largest possible scale, the scale of the entire observable universe, and look at what cosmologists have been finding there. Because the pattern you just saw at the quantum level has an unsettling echo at the cosmological level, and that echo has been getting louder for the better part of 30 years. In 1998, two independent teams of astronomers, teams that were not collaborating, that were in fact in competition with each other, using different telescopes and different methods, were both studying a specific type of exploding star called a Type Ia supernova. These supernovae are extremely useful to cosmologists because they always explode with approximately the same absolute brightness. This makes them what astronomers call standard candles, objects whose intrinsic luminosity you know in advance, so that by measuring how bright they appear from Earth, you can calculate exactly how far away they are. Both teams were using these supernovae to measure how fast the universe is expanding, a question with a known expected answer. The universe has been expanding since the Big Bang. Everyone knew this. The question was only, how fast? And is that expansion slowing down over time? Because of gravity, the mutual gravitational attraction of all the matter in the universe, the expansion should be decelerating. It should be slowing down. Every cosmological model, every piece of theory, every physical intuition all pointed in the same direction. The expansion rate should be decreasing. What both teams found, independently, simultaneously, using different data, was the opposite. The expansion of the universe is not slowing down. It is accelerating. The galaxies are not just moving apart, they are moving apart faster and faster, as if something is actively pushing them away from each other, as if there is a repulsive force operating across the entire fabric of space. This result was so shocking that when both teams first saw it, each assumed the other had made an error. They checked their own data repeatedly, looking for the mistake that must be there. They cross-checked against each other's observations. They brought in additional observers, additional telescopes, additional methods, and every check confirmed the same thing. The universe is not just expanding, it is accelerating, and the force, or whatever it is behind that acceleration, is not predicted by any standard model of physics. Einstein had actually proposed something like it once, a cosmological constant that he later called his greatest blunder. But the value required to explain what the supernova teams found is not the value Einstein played with. It is something far more specific, far more enormous, and far more mysterious. Something that scientists eventually named dark energy, not because they understood what it was, but because they needed a name for the thing they had measured without being able to explain. And dark energy is not a small correction to the existing model. It makes up approximately 68% of the total energy content of the universe. Nearly 7/10 of everything that exists, by energy, is this unknown thing that should not be there. And that is not the only invisible ingredient cosmologists had been forced to add to the recipe of reality. Decades before the discovery of dark energy, astronomers studying the rotation of galaxies had found something equally impossible. When you look at a galaxy, a spiral galaxy like our own Milky Way, you expect the outer parts of the galaxy to rotate more slowly than the inner parts. This is exactly what happens in our solar system. Mercury, which is close to the Sun, orbits much faster than Neptune, which is far away. The further from the center of gravity you are, the slower your orbital speed. This relationship is called Keplerian rotation, and it is a direct and unavoidable consequence of Newton's law of gravity. It is not a subtle prediction. It is one of the clearest and most basic things that gravity does. When astronomer Vera Rubin began measuring the rotation speeds of stars at different distances from the centers of galaxies in the 1970s, she expected to see this pattern. Every star near the center rotating fast, every star near the edge rotating slowly, in a smooth gradient that matched the gravitational influence of the visible mass. What she found was that the rotation curves were flat. Stars at the outer edges of galaxies were rotating at roughly the same speed as stars near the center. In some galaxies, the outer stars were rotating even faster than the inner ones. This should be impossible. Stars rotating that fast at those distances from the galactic center should fly off into intergalactic space. The gravity of the visible matter is nowhere near sufficient to hold them in orbit, and yet they are in orbit. And yet they keep rotating at those impossible speeds in every galaxy Rubin studied. Not in one galaxy, not in two, in every single one. The conclusion, uncomfortable, strange, and yet mathematically inescapable, was that there must be additional mass in these galaxies. Mass that does not emit light, mass that does not interact with electromagnetic radiation of any kind, not visible light, not infrared, not radio waves, not X-rays, mass that is, for all practical purposes, invisible. Scientists called it dark matter, and once astronomers started looking for its gravitational effects, they found it everywhere, around every galaxy, in galaxy clusters, in the large-scale structure of the entire cosmos. Dark matter is not a minor correction. It is not a rounding error. It makes up approximately 27% of the total energy content of the universe. So let us count. Dark energy is 68%. Dark matter is 27%. That leaves approximately 5% for everything else. Every atom, every molecule, every star, every planet, every gas cloud, every black hole, every living thing that has ever existed anywhere in the observable universe. Everything you have ever seen, touched, measured, or described constitutes 5% of what is out there. 95% of the universe is made of things that have no explanation in any currently accepted theory of physics. And this is not a fringe claim. This is the consensus model. This is what mainstream cosmology openly acknowledges every time it publishes a paper about the structure of the universe. 95% unknown. And every attempt to understand what that unknown stuff actually is has, so far, failed. You might be sitting with that for a moment, turning it over, looking for the edge that makes it feel less alarming. Perhaps the missing 95% is just a gap in our instruments, you might think. Perhaps it is a matter of needing better telescopes, more sensitive detectors, more sophisticated analysis, and scientists have certainly taken that approach. For decades, experiments have been designed specifically to detect dark matter directly, to catch one of these invisible particles passing through a detector, colliding with an atom, producing a signal that could be measured. These detectors have been built deep underground in old mines buried beneath mountains, shielded from every known source of background radiation, cooled to near absolute zero, designed with extraordinary sensitivity. The LUX experiment in the United States, the Xenon experiment in Italy, the PandaX experiment in China, each one progressively more sensitive than the last, each one running for years collecting data, waiting for the dark matter signal that the theoretical models predict should be there, that must be there, given how much of it there apparently is, and each one has come back with the same answer: nothing, no signal, no detection, no dark matter particle in any of the mass ranges the leading theoretical models said it should occupy. The detectors are not malfunctioning, the experiments are not flawed, the null result keeps being confirmed. The most sensitive instruments ever built for this purpose keep finding nothing where something should absolutely be. And that pattern, the repeated absence of a signal that must exist, is itself one of the most troubling things in modern physics, because either the detectors are wrong or the models are wrong, and the detectors keep working perfectly on everything else, which means the models might be wrong about what dark matter actually is, even though the evidence that it exists seems overwhelming. Something is there, but it is not what we think it is. At this point in the story, you might begin to feel the shape of something, not just individual anomalies, but a texture to the anomalies, a recurring motif, like a phrase that keeps appearing in different melodies played on different instruments in different rooms. The quantum particles that should not be interfering, the molecules that should not behave like waves, the galaxies that should not be rotating the way they are, the universe that should not be accelerating the way it is, and beneath all of it, the same structure. Something is happening that the equations do not allow, and it keeps happening, not because someone made a mistake, not because the instruments are broken, because reality is producing results that the model says it cannot produce. And the model has been one of the most successful predictive tools ever assembled by human intelligence. So the question that starts to emerge, quietly at first, then with growing insistence, is not what went wrong with the experiment. The question is, what is wrong with the model? And underneath that question, something even more unsettling. What if nothing is wrong with the model? What if reality is simply doing something that our models cannot capture, because our models are built on assumptions about what reality is, and those assumptions are incorrect? Let us move into a different domain entirely, because it is important that you see how widely this pattern spreads. Leave behind the world of particle physics and cosmology. Come into biology, into the chemistry of life itself. Come into the process that your own cells use every single day to turn food into energy, to convert light into thought, to do the astonishingly complex work of being alive. Because there is something happening in the chemistry of life that, when you look at it carefully, should not be happening at the speed and efficiency at which it happens. The process is called photosynthesis, the conversion of sunlight into chemical energy in plants, algae, and certain bacteria. It has been studied extensively for over a century, and its basic chemistry is well understood. But in 2007, a team of researchers at the University of California, Berkeley, published a paper that changed the conversation. They were studying a type of green bacteria that performs photosynthesis, and they used a technique that allowed them to observe what happens inside the photosynthetic complex at an extraordinary level of detail, essentially watching individual molecules in the process of converting light to energy. And what they found was that the energy was moving through the photosynthetic system with a near-perfect efficiency that had no classical explanation. Not high efficiency, near-perfect efficiency. The energy absorbed from a photon was reaching its destination, the reaction center where it gets converted into chemical energy, following a route that visited all possible paths simultaneously, and found the optimal one in a way that no classical diffusion process could replicate in the same time frame. The Berkeley team proposed something that sounded, to many of their colleagues, like an overreach. They suggested that quantum coherence was playing a role in photosynthesis, that the biological machinery of photosynthesis was exploiting quantum effects, the same kind of quantum wave behavior you saw in those double-slit experiments, to achieve its extraordinary efficiency, that plants and bacteria, in the warm, wet, noisy environment of a living cell, precisely the kind of environment where quantum effects are supposed to be immediately destroyed by thermal noise and molecular collisions, were somehow maintaining quantum coherence long enough to use it, to exploit it, to build it into the fundamental machinery of life. This claim was initially met with significant skepticism. Quantum effects in biology, in a warm cell, thermal decoherence should destroy any quantum coherence in femtoseconds, fractions of a trillionth of a second. Life should be purely classical chemistry. And then the same result was confirmed by other teams using other methods. Then similar quantum effects were proposed for other biological processes. Enzyme catalysis, where quantum tunneling appears to allow chemical reactions to occur at rates that classical activation energy barriers should prevent. Then for bird navigation, where certain migratory birds appear to navigate using a quantum compass effect in a molecule called cryptochrome, located in their eyes, which responds to Earth's magnetic field through quantum entanglement between electron pairs. Then for the mechanism by which your nose detects smell, where the leading model now involves not just the shape of odor molecules but the vibrational frequencies of their chemical bonds, detected through a quantum tunneling process in the olfactory receptors of your nose. Life, it seems, is not classical chemistry running on a quantum platform and successfully ignoring the quantum nature of that platform. Life may be actively using quantum mechanics. And that is something that should not be possible in warm, wet, noisy biological systems. The field that studies this is called quantum biology, and it is one of the fastest growing and most contentious areas of modern science, precisely because what it is finding challenges a very deeply held assumption that the quantum world and the biological world are separate, that living things, being large and warm and constantly interacting with their environment, exist entirely in the classical domain, that the quantum weirdness is safely confined to the physicists' laboratories and the theorists' equations, and never intrudes into the world of proteins, cells, and organisms. But the data keeps suggesting otherwise, and each new piece of data is not a wild anomaly produced by a single eccentric lab. It is a confirmed, replicated, peer-reviewed result that survives the scrutiny of an entire scientific community that in many cases was actively looking for the error that would make it go away. The quantum coherence in photosynthesis has been replicated and extended. The quantum tunneling in enzyme catalysis is now textbook material in some biochemistry courses. The radical pair mechanism in bird navigation has been demonstrated in multiple species. The findings are not going away. They are multiplying, and the more they multiply, the more insistently that central question reasserts itself. Is this a series of coincidences, or is this a pattern? Is life somehow organized around quantum effects? Is quantum mechanics not just the microscopic foundation of chemistry, but an active ingredient in the complex chemistry of living systems? And if so, why and how? And what does it mean for everything we thought we understood about the boundary between physics and biology? But you have not yet heard about the thing that keeps many physicists awake at night more than any of these individual anomalies. You have not yet heard about the measurement problem, because the quantum interference experiments and the quantum biology results and the dark matter puzzles and the dark energy mystery, all of these are strange, all of them are unsolved, but none of them carry quite the same philosophical weight as what happens when you try to make a quantum measurement. Let us go back to that single electron being fired at the double-slit barrier. We established that it travels as a wave of probability, passing through both slits, interfering with itself, producing a pattern consistent with wave behavior. Now, add one more element to the experiment. Place a detector at one of the slits, a small sensor that will tell you which slit the electron actually passed through. You want to know. You want to observe. Surely the electron has to pass through one slit or the other. Surely if you just look carefully enough, you can determine which path it took without disturbing anything in any meaningful way. You add the detector, you run the experiment, and the interference pattern disappears. Not because the detector blocked the electron, not because the electron changed its path, but because the act of measuring, the act of gathering information about which slit the electron went through, collapses the wave function. The electron, which was previously traveling as a probability wave exploring all possible paths, instantly becomes a definite particle at a definite location taking a definite path, and the interference, which depended on the wave traveling all paths simultaneously, vanishes completely. This is the measurement problem, and it is not a solved problem. It is one of the deepest and most contentious unresolved questions in physics. What exactly causes the collapse? What is the role of the observer? At what point does a quantum superposition, a state of being many things at once, become a classical, definite state? Is it the detector? Is it the information extracted? Is it consciousness? Is it some threshold of physical complexity? Is there no collapse at all, but rather a branching of reality into multiple histories, what some call the many worlds interpretation, so that the electron does not choose a path, but rather the universe splits and in one branch it went through the left slit and in another it went through the right? These are not fringe questions debated by eccentric philosophers. These are the interpretations of quantum mechanics that practicing physicists actually argue about in peer-reviewed journals and at major conferences. The Copenhagen interpretation, the many worlds interpretation, the pilot wave theory, the relational interpretation, the consistent histories approach. After nearly a century of quantum mechanics, after all the extraordinary predictive success of the theory, there is no consensus, none, on what quantum mechanics actually means about the nature of reality. The equations work. The predictions are accurate to a precision that has no parallel in the history of science. But the story about what is really happening, about what reality is actually doing when it is not being measured, is completely unresolved. And here is the unsettling part. Every interpretation that physicists have proposed, every attempt to tell a consistent story about quantum reality, requires making an assumption that seems deeply strange or deeply contrary to our ordinary sense of what the world is. None of them are comfortable. None of them resolve the strangeness. They only relocate it. In the many worlds interpretation, every quantum event splits the universe into multiple parallel branches. Every time an electron passes through a slit, the universe forks, and in different branches, different outcomes are recorded. This means there are an unimaginably vast and constantly growing number of parallel universes, each one as real as ours, each one containing versions of you, of this planet, of this entire cosmos, differing only in the outcomes of quantum events. This is not a science fiction idea. This is a serious, mathematically consistent interpretation of quantum mechanics advocated by serious, mathematically sophisticated physicists, including Hugh Everett, who formulated it in 1957, and a large community of researchers today. It makes the same predictions as standard quantum mechanics, resolves the measurement problem elegantly, and requires accepting that reality is incomprehensibly larger and stranger than any human being can actually comprehend. In the pilot wave interpretation, particles always have definite positions and velocities, but they are guided by a real, physical wave that travels through space alongside them, a wave that responds to the entire experimental configuration instantaneously, explaining how a particle knows about both slits simultaneously. This wave is real, physical, and travels faster than light, which directly conflicts with the special theory of relativity. In the Copenhagen interpretation, the most widely taught version of quantum mechanics, questions about what is happening between measurements are simply declared meaningless. Reality does not have a definite state between observations. The act of measurement creates the definite outcome. Nothing exists in any determined sense until it is observed. This last interpretation, the orthodox view for most of the 20th century, is perhaps the most deeply disturbing of all, because it implies that the universe at its most fundamental level does not have a definite existence independent of observation. It implies that reality might be, in some sense, observer-dependent. And while physicists argue about whether this is a literal ontological claim or merely an epistemic one, the data keep supporting the formal structure of quantum mechanics with no sign of which interpretation, if any, is correct. The universe is giving us equations that work perfectly and a story that makes no sense. Now let us introduce something that is, in many ways, the strangest single result in the history of experimental science. and certainly the one with the most unsettling implications for everything you have just been considering. It is a phenomenon called quantum entanglement, and the story of how scientists came to accept it is, by itself, a story about what happens when the data keeps contradicting what should be possible until the weight of evidence finally becomes impossible to deny. Quantum entanglement was first discussed by Albert Einstein, Boris Podolsky, and Nathan Rosen in a famous 1935 paper, typically referred to as the EPR paper, in which they intended to show that quantum mechanics was incomplete. Here was their argument. Quantum mechanics predicts that two particles can be prepared in a correlated state, such that measuring one particle instantly determines the state of the other, regardless of how far apart they are. Einstein, Podolsky, and Rosen argued that this was absurd, that it implied in spooky action at a distance that violated the principle of locality, the principle that no influence can travel faster than light, and that what happens at one location cannot instantly affect what happens at a distant location. Their paper was not intended as a confirmation of quantum mechanics. It was intended as a reductio ad absurdum, an argument that quantum mechanics must be incomplete because if it were correct, it would require this insane-sounding instant correlation between distant particles. They thought the argument would either prompt theorists to fix quantum mechanics or expose its fundamental incompleteness. For nearly 3 decades, this remained a philosophical puzzle with no clear experimental resolution. Then in 1964, physicist John Bell published a paper that changed everything. Bell showed that the question, whether quantum correlations between distant particles are due to some hidden local mechanism, as Einstein believed, or due to genuine non-local quantum effects as quantum mechanics requires, could be tested experimentally. He derived a set of mathematical inequalities that any hidden local variable theory must satisfy. If experiments violated these inequalities, it would mean that no local hidden variable theory could explain the correlations, and that quantum mechanics, with its non-local entanglement, was actually correct. The first decisive experiments were performed by John Clauser in the 1970s, and then, most importantly, by Alain Aspect and his colleagues in France in 1982. Aspect's experiment measured the polarization correlations between pairs of photons produced simultaneously and sent in opposite directions. The photons traveled far enough apart that no signal traveling at the speed of light could connect them during the measurement, and the correlations between their polarizations consistently violated Bell's inequalities. The photons were not just correlated because of some shared property they carried when they were created. The correlations were stronger than any local mechanism could produce. The measurement of one photon's polarization was instantaneously influencing the outcome of the other photon's polarization measurement, regardless of the distance between them. Einstein was wrong. But let us be precise about what Einstein was wrong actually means here, because the implications deserve to be unpacked very carefully, and because the temptation to minimize them is strong and understandable. Einstein was not wrong about relativity. He was not wrong about the speed of light as a limit for the transmission of information or energy. What he was wrong about was locality, the assumption that the universe is composed of separate, independent parts that can only influence each other through physical signals traveling at finite speeds through the space between them. Bell's theorem and Aspect's experiments together proved that this assumption, one of the most intuitive and deeply held assumptions in all of physics, one that feels less like a theory and more like a basic feature of what it means for things to exist as separate entities, is incorrect. The universe is, at some fundamental level, non-local. Distant parts of reality are connected in a way that does not require any signal to travel between them, in a way that does not diminish with distance, in a way that appears to operate outside the ordinary causal structure of space and time. And this is not a result that has faded with time or been qualified into near meaninglessness by subsequent research. It has been strengthened. Decade after decade, more sophisticated experiments have closed loophole after loophole that skeptics proposed as escape routes. The detection loophole, the locality loophole, the freedom of choice loophole. In 2015, a team at Delft University in the Netherlands performed a loophole-free Bell test, an experiment so carefully designed that no combination of local hidden variables and experimental imperfections could explain the result. The violation of Bell's inequalities was confirmed again, completely, cleanly, without ambiguity. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics specifically for their work on entanglement and Bell inequality violations. The Nobel Committee does not award prizes for fringe results. The non-locality of the universe is now official, mainstream, prize-winning physics, and it remains completely unexplained in any intuitive, mechanical, story-like sense. We know it happens. We can measure it with extraordinary precision. We have no idea what it means for the nature of reality. You might notice something about the way this sequence of discoveries feels. Each new result does not replace the strangeness of the last one. Each new result adds to it, layers on top of it, deepens it in a way that compounds rather than resolves. The quantum wave behavior of particles, the persistence of quantum effects into unexpectedly large objects, the quantum coherence in biological systems, the measurement problem and the observer effect, and now the non-locality, the instantaneous correlation of distant particles with no mechanism for communication between them. These are not separate mysteries that happen to be in the same category. They are facets of the same underlying problem, which is that the universe, at its most fundamental level, does not behave like a collection of separate, local, definite, classical objects interacting through well-defined forces. It behaves like something else, something that our current conceptual vocabulary does not have adequate words for. And the feeling that starts to grow as you sit with all of this is not the comfortable feeling of unsolved puzzles, waiting for the right scientist to come along and solve them. It is the more unsettling feeling of a framework straining against its own limitations, of a model that has been extraordinarily successful, but that is beginning to show the signs of something deeper than gaps in knowledge. What it is beginning to show is the signs of gaps in conception, not missing facts but missing ideas, not incomplete data, but an incomplete understanding of what reality fundamentally is. Let us shift registers again. Let us come up to the human scale, not to the microscopic world of quantum particles, and not to the cosmological scale of galaxies and dark energy, but to the intermediate scale where you live, where the laws of classical physics are supposed to reign with complete and reassuring stability. Because there are things happening at this intermediate scale too, things that keep appearing in experimental data, things that keep surviving attempts to explain them away, that suggest the strangeness is not confined to the extremes of size and scale. One of the most quietly disturbing of these is the phenomenon of anomalous water structure. You know water. You have lived with it your entire life. You know that it is a liquid at room temperature, that it flows, that it freezes at 0 degrees Celsius and boils at 100 degrees Celsius at sea level. You know that its molecules, 2 hydrogen atoms bonded to 1 oxygen atom, interact with each other through hydrogen bonds to form the familiar properties of the liquid you drink. You know this because it has been studied in extraordinary detail for well over a century. Water is one of the most thoroughly characterized substances in all of chemistry. And yet, in experiments first published in 2008 and subsequently replicated and extended, researchers studying water in extremely confined spaces, between 2 flat surfaces separated by distances of just a few nanometers, found that the water formed a structure different from anything in its known phase diagram. Not liquid, not ice, not any of the multiple known phases of solid water, something that had the flow properties of a highly viscous liquid and the structural properties of a gel, but that was neither. Something that persisted across a range of temperatures where normal water is simply a liquid. Something that seemed to represent a previously unknown state of matter for one of the most studied substances in all of science. The result was controversial, and the debate continues. But the experimental signature of this unusual water structure has been observed repeatedly by multiple independent groups in multiple experimental configurations. It does not go away when you look more carefully. It becomes more clearly defined. And while we are discussing water and its anomalies, let us mention something else that water does, something that has been quietly perplexing materials scientists for decades, and that almost never makes it into popular discussions of scientific mysteries. Water, as you know, is less dense as a solid than as a liquid. Ice floats. This is unusual. Most substances are denser in their solid form than in their liquid form, because the solid phase packs atoms or molecules more tightly. Water does the opposite. Below 4 degrees Celsius, liquid water expands as it cools instead of contracting. This anomaly is why ice floats, which is why oceans do not freeze solid from the bottom up, which is why aquatic life survives winters, which is one of the conditions that made complex life on Earth possible. This is not merely interesting. It is existentially important to everything alive on this planet. And while the basic explanation in terms of hydrogen bonding is well known, the precise mechanism by which water exhibits this and approximately 72 other known physical and chemical anomalies that collectively make it the most unusual common substance in nature, is still not fully understood. Water, the substance that makes up roughly 60% of your body, the substance that covers most of the surface of this planet, the substance you require to survive, continues to surprise the scientists who study it most carefully. It keeps doing things that the models say it should not quite be doing, in ways that are too subtle for headlines but too persistent for dismissal. But let us not dwell too long on water, because there are more alarming examples waiting, and because each new example is not just interesting in isolation, it is another instance of the same pattern, another data point in the accumulating evidence that the universe has not finished revealing the full extent of its strangeness. Let us talk about the anomalous results that have been emerging from neuroscience, from the scientific study of how the brain generates experience. Because here, at the intersection of biology and consciousness, there is a pattern of impossible observations that has been building for decades, and that carries implications not just for neuroscience, but for the most fundamental questions about the nature of mind and reality. This study of near-death experiences is a good entry point because it is simultaneously one of the most studied and one of the most dismissed areas of anomalous research. Near-death experiences, the structured, vivid, often transformative experiences reported by people who have come close to death or been clinically dead for a short period, have been documented across cultures, across time periods, and across medical contexts for as long as people have been recovering from life-threatening events. They were studied seriously by Raymond Moody in the 1970s, generating enormous public interest. They were then largely dismissed by the scientific mainstream as hallucinations produced by a dying brain, as the artifacts of cerebral hypoxia, as the brain misfiring under extreme physiological stress. That explanation was comfortable, and for a time it seemed adequate. Then, in 2001, the British medical journal The Lancet, one of the most prestigious medical journals in the world, not a fringe publication, published a prospective study of near-death experiences conducted by cardiologist Pim van Lommel and his colleagues in the Netherlands. The study followed 344 cardiac arrest patients who were resuscitated after being clinically dead. No heartbeat, no brain activity, pupils dilated, no measurable electrical activity in the brain. 18% of these patients reported clear, structured, detailed near-death experiences. Some reported veridical perceptions, observations of events in the resuscitation room that were later confirmed as accurate by the medical staff present, observations that occurred during the period when the patients had no detectable brain activity. The patients reported seeing the room from above, described specific actions taken by specific medical personnel, described details of the physical space that they could not have seen from their position on the resuscitation table. And this happened during the period when their brains, by every available measure, were not generating the kind of electrical activity needed to support conscious experience. Van Lommel's study was not anecdotal. It was prospective, controlled, and published in the most rigorous medical context available. And it raised a question that neuroscience has not resolved. If consciousness is purely a product of brain activity, and if brain activity is absent, then how is any experience occurring at all? The dominant neuroscientific model says it cannot, and yet the data says it is. The same question, in a different form with different data in a different scientific context, has been reverberating through consciousness research for even longer. The hard problem of consciousness, as formulated by philosopher David Chalmers in 1995, is the problem of explaining why any physical process gives rise to subjective experience at all. Why does it feel like something to be you? Why is there an inner experience accompanying the neural computation in your brain? Neuroscience can tell you which brain regions are active when you see the color red, which neurons fire when you feel pain, which circuits are engaged when you experience joy. It can map the correlations between physical brain states and experiential states with extraordinary precision, but it cannot tell you why any physical process produces experience at all, rather than simply processing information in the dark, as a computer presumably does. Why is there something it is like to be a conscious being, rather than simply neural activity occurring without any accompanying inner life? This question has not been answered by any neuroscientific theory, not even approximately answered. Every theory of consciousness proposed, from global workspace theory to integrated information theory to predictive processing models, explains what consciousness does, what it correlates with, what functions it performs. None of them explain what consciousness is, why physical processes should give rise to subjective experience, or how the inner world of experience relates to the outer world of matter. The hard problem remains, as Chalmers originally described it, genuinely hard. And some of the most serious researchers in the field now argue that it is not merely a difficult empirical question waiting for more data, it is a conceptual puzzle, that may require a fundamental revision of our understanding of what matter is, what mind is, and how they relate to each other. And this is where the threads begin to pull together in a way that starts to feel less like a collection of separate puzzles and more like a single, coherent, deeply unsettling pattern. Think about what you have accumulated in this story so far. Quantum particles that behave as waves of probability until measured, at which point they collapse into definite states. And the collapse process, the mechanism of measurement, remains unexplained after a century of effort. The non-locality of entangled particles, demonstrating that the universe is not composed of separate, locally connected pieces in the way that all ordinary intuition assumes. The persistence of quantum effects into unexpectedly large objects, suggesting that the boundary between quantum and classical is not where the textbooks place it. Quantum coherence in biological systems, suggesting that life has found a way to use quantum mechanics in warm, wet environments where quantum effects should not survive. The dark matter and dark energy that make up 95% of the universe and that remain, despite decades of searching, completely undetected in any direct way. The accelerating expansion of the universe, driven by a force that has no explanation in any accepted theory. The near-death experiences that occur during periods of zero measurable brain activity. The hard problem of consciousness that no theory of physical processes has yet addressed. Each of these individually is a major unsolved problem. Together they are something more. Together they form a portrait of a universe that is systematically producing results that contradict the foundational assumptions of the model that has been used to understand it, not occasionally, not rarely, repeatedly, persistently, across every scale, every domain, every field of science. And there is something about the way these problems keep appearing that is worth dwelling on for a moment, because it speaks to something about the nature of the scientific process itself. When scientists encounter an anomalous result, they have a very specific set of responses available to them. They can dismiss it as error and try to identify the source of the mistake. They can acknowledge it as a genuine anomaly and file it away as an unsolved problem while continuing to work within the existing framework. They can try to modify the existing framework just enough to accommodate the anomaly without disturbing the rest of the structure. Or they can conclude that the anomaly reveals a fundamental inadequacy in the existing framework and attempt to build a new one from scratch. In the history of science, the first three responses are overwhelmingly more common than the fourth. Scientists are not revolutionaries by default. They are trained to trust the framework that has been built over generations of successful work, and they are right to be skeptical of any single result that seems to demand a revolution. The fourth response, genuine paradigm change, requires the weight of many anomalies accumulating over a long period, the failure of all incremental fixes to adequately resolve them, and usually a new conceptual idea powerful enough to explain not just the anomalies but everything the old framework explained, plus more. The pattern that is building throughout this story, across quantum mechanics, cosmology, biology, neuroscience, looks very much like the pattern that precedes that fourth response. The anomalies are not resolving. The incremental fixes are not sticking. The framework is not absorbing the new results without distortion. Something is building, something is accumulating, and the feeling that comes with recognizing that is not the comfortable feeling of normal scientific progress. It is the vertiginous feeling of standing at the edge of a very large revision. Let us now go somewhere that most mainstream science discussions carefully avoid, not because the evidence is absent, but because the implications are too uncomfortable for the framework of conventional academic discourse. Let us talk about the anomalous signals. Because scattered throughout the history of scientific observation, there is a class of events that resist explanation, not because they are subtle or ambiguous, but because they are extremely clear signals from the data that something is there, something that no known physical process accounts for, and they keep appearing in multiple independent datasets, gathered by multiple independent teams, using multiple independent methods. The first of these is perhaps the most famous, the WOW signal. In 1977, astronomer Jerry Ehman was working at the Big Ear radio telescope at Ohio State University, scanning the sky for artificial radio signals as part of the SETI program, the search for extraterrestrial intelligence. On August 15th, the telescope recorded a signal of such extraordinary intensity and precision that when Ehman reviewed the computer printout, he circled it in red ink and wrote, "Wow," in the margin. The signal lasted exactly 72 seconds. The full window of time during which the telescope's fixed beam could observe any given region of the sky as Earth's rotation carried it past. Its frequency was close to 1420 megahertz, the frequency at which hydrogen naturally emits radio waves, the frequency that had been theorized as the most likely channel for interstellar communication, precisely because any technologically sophisticated civilization would know that hydrogen is the most abundant element in the universe and would recognize 1420 MHz as a meaningful, universally recognizable frequency to use. The signal was extraordinarily strong, 30 times the background noise level, and it came from the direction of the constellation Sagittarius, from a region of space that contains no known natural radio source capable of producing a signal with those characteristics. The WOW signal has never been convincingly explained. Astronomers have observed that region of sky thousands of times since 1977, with the same telescope and with more sensitive instruments, and the signal has never been detected again. Various natural explanations have been proposed over the years: a comet with an unusual hydrogen cloud, a peculiar atmospheric reflection, an instrumental artifact, and each has been examined and found inadequate. The comet hypothesis, proposed in 2016, required the comet to be in exactly the right position at exactly the right time and to have hydrogen cloud properties that no other known comet possesses. It was proposed as a plausible candidate explanation, but it has not been accepted as definitive by the SETI community or by most radio astronomers. The signal remains, 47 years later, unexplained. It was a single observation of something that should not, by any current understanding, be there. And unlike a laboratory experiment, it cannot be repeated. The universe does not rerun its experiments on command. But the WOW signal is not the only anomalous signal in the catalog of observations. It is merely the most famous, because in 2007, a completely different type of cosmic signal was discovered, and this one keeps repeating. Fast radio bursts, or FRBs, are among the most energetic and mysterious phenomena in modern astronomy. They are extremely brief, lasting milliseconds, but extraordinarily powerful bursts of radio waves coming from cosmological distances, from billions of light years away. The first was discovered in 2007 by Duncan Lorimer and his student David Narkovich, who were reviewing archival data from the Parkes Radio Telescope in Australia, and found a burst so intense that it had saturated the detector. Initially, it was thought to be instrumental artifact, something the telescope had done rather than something the universe had done. But the dispersion of the signal, the way different frequencies arrived at slightly different times in a pattern consistent with the signal having traveled through the diffuse plasma of intergalactic space for billions of years, told a different story. This was a real signal from a real source, a signal with more energy than the sun releases in an entire day, packed into a few milliseconds. A signal from a source so distant that its light has been traveling since long before the Earth existed, and then more of them were found, not just one FRB but hundreds, then thousands, as telescopes became more sensitive and survey programs more systematic. Some of them repeat, the same source producing multiple bursts. Some of them produce bursts in patterns that appear, tantalizingly, almost periodic, almost as if they are coming from something that is rotating, or orbiting, or otherwise cycling through a regular rhythm. And the sources of FRBs, while now generally attributed to exotic objects like magnetars, highly magnetized neutron stars, remain poorly understood, with several observed properties that do not fit neatly into any single theoretical model. The universe keeps sending these signals. The signals keep defying simple explanation, and the pattern of defiance keeps accumulating. But the anomalous signals are not only coming from space, they are also appearing in particle physics, at the most fundamental level of matter, in experiments so carefully designed and so precisely executed that the word impossible is the only word that fits the situation. In 2021, the Muon G2 experiment at Fermilab in the United States published results that sent a ripple of barely contained excitement and barely contained alarm through the physics community. The experiment was measuring a property of the muon, a fundamental particle similar to the electron but much heavier, called its anomalous magnetic moment. This is a quantity that quantum field theory, the most precise physical theory ever constructed, predicts with extraordinary accuracy. The theoretical prediction is so precise that it extends to 10 decimal places. The experimental measurement is equally precise, and the two did not agree. The muon was wobbling at a rate slightly faster than the standard model of particle physics predicted it should. The discrepancy was not enormous, it was in the 10th significant figure, but the statistical significance was enough to suggest that something was influencing the muon that the standard model does not include, something unknown. Something that interacts with the muon in a way that has not yet been discovered. The The Standard Model is the most comprehensively tested physical theory in history. It describes the behavior of every known fundamental particle and every known force except gravity with extraordinary accuracy. And the muon G2 result suggested that it was missing something, that there is a particle, or a force, or a physical process that exists in nature, but is not in the model. Not a small correction, a fundamental absence. The muon G2 result was not the first hint of this kind. The Standard Model has been quietly accumulating anomalies for years. There are the so-called B-meson anomalies, measurements of the decay products of B-mesons, a type of composite particle containing a bottom quark, that have shown hints of violating a principle called lepton universality, which says that electrons, muons, and tau particles should behave identically in electromagnetic interactions, except for their different masses. The anomalies suggested, with varying degrees of statistical confidence over multiple experiments, that muons and electrons were not behaving identically, that the universe was treating them differently, in a way the Standard Model absolutely forbids. The LHCb experiment at CERN has been one of the primary sites for measuring these anomalies, and results released across 2021 and 2022 caused enormous excitement and concern. Some of the anomalies became less statistically significant as more data was collected, reducing confidence in them as genuine new physics signals, but others remained. The picture is not clean. The data is not saying one clear thing. It is saying something complicated and unresolved, and the sum total of the hints taken together across multiple experiments and multiple decay channels suggests something that continues to resist the comforting explanation that it is all just statistical fluctuation and measurement error. The Standard Model is stressed. It is being pushed on at multiple points simultaneously, and the stress is not going away. Then there is the matter of the Hubble tension, a problem in cosmology that has been escalating in severity for about a decade, and that now represents one of the most pressing crises in fundamental physics. The Hubble constant is the rate at which the universe is expanding. It is one of the most important numbers in cosmology, and there are two very different methods for measuring it. The first method looks at the early universe, at the cosmic microwave background radiation, the faint afterglow of the Big Bang, which has been mapped with extraordinary precision by the Planck satellite. Using the pattern of tiny temperature fluctuations in this radiation, cosmologists can calculate the Hubble constant based on the physics of the very early universe. The second method looks at the local universe, measuring distances to galaxies using standard candles like Cepheid variable stars and Type Ia supernovae, and using those distance measurements combined with redshift measurements to calculate how fast the universe is expanding today. These two methods should give the same answer. They are measuring the same constant. The universe only expands at one rate, and yet they do not give the same answer. The value obtained from the cosmic microwave background is approximately 67.4 kilometers per second per megaparsec. The value obtained from local measurements is approximately 73 kilometers per second per megaparsec. That is a discrepancy of nearly 10%. And over the past decade, as both measurements have become more precise, the discrepancy has not shrunk. It has grown larger and more statistically significant. The two values are now separated by more than 5 sigma, the standard threshold for claiming a discovery in physics. If this were a laboratory result, a 5 sigma discrepancy between two independently measured values of the same quantity would be considered definitive evidence that something was wrong with the models underlying one or both measurements. Either the physics of the early universe is different from what the Planck analysis assumes, or the local expansion rate measurements have a systematic error that no one has yet identified, or, and this is the option that keeps the cosmologists awake, the Standard Model of cosmology is missing something fundamental. Let us pause here and take stock of what has been accumulating, because you have now heard enough to start feeling the full weight of the pattern. You have the quantum mechanical results, double slit interference, entanglement, the measurement problem, the quantum to classical transition problem, all of which point toward a fundamental inadequacy in our understanding of the nature of physical reality at the microscopic scale. You have the biological results, quantum coherence in photosynthesis, quantum tunneling in enzymes, quantum effects in bird navigation, and possibly in olfaction, all of which point toward quantum effects playing a role in life at a scale where they should not survive. You have the cosmological results, dark matter, dark energy, the accelerating expansion, the Hubble tension, all of which point toward a universe that is 95% unknown and that is expanding in a way that no accepted theory explains. You have the particle physics results, the muon G2 anomaly, the B-meson anomalies, the hints of new physics beyond the standard model, all of which point toward fundamental particles behaving in ways that the most successful physical theory ever constructed says they cannot. You have the consciousness results, near-death experiences with veridical perceptions during zero brain activity, the hard problem of consciousness with no theoretical resolution in sight, all pointing toward the possibility that the relationship between mind and matter is fundamentally different from what the standard neuroscientific model assumes. And now you have the anomalous signals, FRBs, the wow signal, the various unexplained cosmic events, pointing toward a universe full of phenomena that no current model accounts for. This is not one problem. This is not two problems. This is a cascade, a simultaneous challenge to the foundations of physics, chemistry, biology, cosmology, and neuroscience, all appearing at the same historical moment, all resisting the same kinds of explanations, all pointing in a direction that has no comfortable name yet. Scientists, being scientists, are not of one mind about any of this. And it is important to understand the spectrum of responses that exist within the community of people who study these things professionally, because the range of those responses is itself revealing. At one end of the spectrum are those who remain fully confident that all of these anomalies will eventually be resolved within the existing framework, that they represent gaps in knowledge rather than gaps in conception. Dark matter will be detected eventually. The detectors just need to be more sensitive. Dark energy will be explained when a complete theory of quantum gravity is developed. The muon G2 anomaly will turn out to be a subtle experimental error, or will reveal a new particle that slots neatly into an extended version of the standard model. The quantum to classical transition will be fully explained by decoherence once we understand the process better. Consciousness will be explained by neuroscience once the relevant circuits and mechanisms are mapped with sufficient precision. These scientists are not dismissing the anomalies. They are contextualizing them within a tradition of scientific progress where hard problems eventually yield to patient, rigorous investigation. And they have the entire history of science on their side, because that tradition is real, and it has a remarkable track record. At the other end of the spectrum are those who argue, carefully, formally, with supporting arguments published in major journals, that the accumulation of these anomalies is telling us something that incremental progress cannot fix, that what we are seeing is not gaps in knowledge but genuine limits of a conceptual framework, that the model of reality built on a foundation of local, definite classical matter interacting through well-defined forces in a three-dimensional space and one-dimensional time, the intuitive picture that underlies not just pre-quantum physics, but much of the intuition that guides even contemporary physics, is fundamentally wrong, not incomplete in a way that can be fixed by adding a new particle here, a new force there, wrong in a way that requires building a new foundation. Physicists like Lee Smolin, who has argued for years that the foundational problems of quantum mechanics reveal a deep inadequacy in our conception of time and causality. Roger Penrose, who argues that consciousness cannot be explained by computation or neural activity, and that quantum gravity plays a role in generating subjective experience. Nima Arkani Hamed and others developing the amplituhedron, a mathematical structure that suggests space-time itself might not be fundamental, but might be an emergent feature of a deeper reality that has no spatial or temporal structure. Carlo Rovelli, whose relational quantum mechanics reframes reality not as a collection of objects with properties, but as a web of relationships and interactions with no view from outside. These are not cranks. These are leading physicists grappling seriously with the possibility that the foundation needs to change, not just the superstructure. In the middle of this spectrum, which is where most working scientists exist, in a state of productive uncertainty that neither dismisses the anomalies nor overclaims their significance, there is a quality of intellectual suspense that is unique to this particular historical moment. Because in the history of science, there have been other periods of anomaly accumulation that preceded revolutionary change. In the late 1800s, there were several well-known experimental results that classical physics could not explain. The ultraviolet catastrophe in blackbody radiation, the photoelectric effect, the null result of the Michelson-Morley experiment that found no evidence for the luminiferous ether. Each of these was, individually, a puzzle. Together they were the signs of a revolution that would produce quantum mechanics and relativity in the first decades of the 20th century. Looking back from the present, it seems obvious that those anomalies were pointing towards something big. But to the scientists living through that period, to people like Lord Kelvin, who in 1900 famously said that there was nothing new to be discovered in physics except in two small clouds on the horizon, the very clouds that became quantum mechanics and relativity. It did not feel obvious at all. It felt like normal science dealing with normal problems. The revolution was not announced. It arrived. And there is a serious argument to be made that the accumulation of anomalies we are currently experiencing, the quantum weirdness, the dark sector, the Hubble tension, the quantum biology, the consciousness puzzle, represents a similar moment. A new set of small clouds on the horizon, each one individually explicable with enough effort, but collectively pointing towards something that the existing framework cannot accommodate. Let us now go into one of the most unusual territories that mainstream science has recently begun to take seriously, a territory that would have been considered pure speculation 2 decades ago, but that has become the subject of serious research publications and conference presentations at major institutions. It is the question of whether the universe itself might be, in some sense, computational, whether the physical world has properties more consistent with a simulated or information-theoretic substrate than with a purely material one. This is the simulation hypothesis in its more rigorous, more scientifically grounded form, not the dramatic pop science version about video games, but a carefully reasoned argument about the relationship between information, computation, and physical reality. The argument begins with a simple observation. The universe, at its most fundamental level, appears to be digital rather than continuous. Quantum mechanics describes physical quantities as coming in discrete units, quanta. Space itself, at the Planck scale, may have a minimum granularity, a smallest possible length, approximately 10 to the power of -35 meters, below which the concept of distance may lose meaning. Energy comes in discrete packets. Spin comes in discrete values. Time at the Planck scale may be discrete as well. The universe appears to have a maximum information density, a finite number of bits of information per unit volume, described by the Bekenstein bound. And the behavior of quantum systems is described by mathematical operations that bear a striking resemblance to the operations of information processing, unitary transformations, measurement operations, the evolution of probability amplitudes in ways that parallel the logic of computation. Physicist John Archibald Wheeler captured this idea with his famous phrase, "it from bit," the suggestion that the physical world might be, at its foundation, made of information rather than matter. That every particle, every field of force, even the space-time continuum itself, derives its existence from the answers to yes or no questions. This was a philosophical speculation when Wheeler proposed it in 1989. Today, it has developed into a serious research program in fundamental physics. The field of quantum information theory has revealed deep connections between quantum mechanics and information processing that go beyond mere analogy. The holographic principle, one of the most well-supported ideas to emerge from string theory and quantum gravity research, suggests that all the information contained in a volume of space can be encoded on the 2-dimensional boundary of that volume. This means that the 3-dimensional world you perceive might, in a physically precise sense, be a kind of projection of a 2-dimensional informational structure, not an illusion exactly, but a holographic encoding, where the apparent 3rd dimension is an emergent feature of a reality that is, at its foundation, flat. This is not a fringe idea. The holographic principle was first proposed by Jacob Bekenstein and Stephen Hawking in the context of black hole thermodynamics, developed by Gerard 't Hooft and Leonard Susskind into a general principle of quantum gravity, and found its most concrete mathematical expression in the anti-de Sitter conformal field theory correspondence discovered by Juan Maldacena in 1997, one of the most cited papers in the history of physics. Space-time might be holographic. Reality might be, in some technically precise sense, an encoding. And that word, encoding, carries implications that are difficult to sit with comfortably for very long. Because if physical reality is fundamentally informational, if the universe at its base is a structure of information being processed according to rules, then the boundary between physical reality and computation begins to blur in a way that is genuinely disorienting. Not in the lazy sense of, perhaps we are living in a video game, but in the deeper and more serious sense that the properties we associate with physical reality, solidity, extension, causality, the arrow of time, might be emergent features of an underlying informational process rather than fundamental ontological facts about the nature of existence. And if that is the case, if space and time and matter are emergent rather than fundamental, then many of the impossible results we have been discussing start to look less like violations of physical law and more like features of a substrate that our current physical laws do not describe at a deep enough level. The non-locality of quantum entanglement, for instance, is less surprising if the apparent spatial separation between entangled particles is not a fundamental feature of the substrate, but an emergent property of the information encoding. Two particles that appear to be far apart in the emergent spacetime might be, at the level of the underlying informational structure, adjacent or interconnected. The separation is real within the space that emerges, but at the level of the deeper substrate, the information is connected. And what looks like instantaneous non-local correlation in the emergent spacetime is, at the substrate level, simply a local connection. This is not proof of anything, but it is a framework, one being explored seriously by physicists like Eric Verlinde, who has argued that gravity itself is an emergent entropic force rather than a fundamental interaction that resolves some impossibilities by relocating them into a different ontological layer. It becomes extremely difficult to formulate coherently. You cannot have information without a context in which that information is meaningful. And that context requires something that functions like awareness, like observation, like the capacity to register a state of affairs. This does not mean the universe requires human consciousness to exist. That would be a wild and unjustified leap. But it does mean that if you follow the informational interpretation of physics to its logical conclusion, you find yourself in territory where the absolute separation between observer and observed, between mind and world, between consciousness and physical reality, begins to dissolve. And that dissolution is not comfortable, because it means the anomaly in the neuroscience data, the consciousness that persists during zero brain activity, the hard problem that no physical theory resolves, is not a separate puzzle from the anomalies in quantum mechanics and cosmology. They are the same puzzle, appearing in different rooms of the same building, all connected by the same corridor that no one has yet fully mapped. Let us talk about time, because time is one of those things that feels so obvious, so immediate, so inescapably real that the suggestion that our understanding of it might be fundamentally wrong seems almost absurd. You experience time constantly. You live inside it. You remember the past and anticipate the future. The arrow of time, the asymmetry between past and future, the fact that time flows in one direction and not the other, is one of the most viscerally certain features of your existence. And yet time is one of the most persistently problematic concepts in all of fundamental physics. The equations of classical mechanics are time-symmetric. They work equally well forward and backward in time. If you filmed a collision between two billiard balls and played the film in reverse, the reversed film would show a physically valid event that violates no law of classical mechanics. The same is true for quantum mechanics. The same is true for general relativity. The fundamental equations of physics do not have a preferred direction of time. They do not encode the arrow of time that you experience. The asymmetry between past and future is not built into the laws. It has to be explained from somewhere else, and the leading explanation is thermodynamic, based on the second law of thermodynamics, which says that entropy, the degree of disorder in a system, increases over time. Things become more disordered over time because there are vastly more disordered states than ordered ones, and random processes are statistically far more likely to move a system toward greater disorder than toward greater order. But here is the problem with that explanation. For the second law to explain the arrow of time, you need to explain why the universe started in an extremely low entropy, highly ordered state, the Big Bang. Because if entropy is always increasing, then in the past it was lower, and further in the past it was lower still, until you reach the beginning of time when it was at its minimum. Why was the initial state of the universe so extraordinarily ordered? Why did the Big Bang produce a configuration of matter and energy so improbably smooth, so precisely balanced, so beautifully tuned for entropy to increase in the way it has? This is not a trivial question. The physicist Roger Penrose has calculated that the probability of the universe starting in a state as ordered as the one implied by the Big Bang, if you imagine randomly selecting an initial configuration from all possible configurations consistent with the current observed state, is 1 in 10 to the power of 10 to the power of 123. That is not just an astronomically small probability. It is a number so far beyond astronomical that it has no meaningful comparison in the physical world. A number so extreme that if you were to write it out, the number of zeros required would exceed the number of particles in the observable universe by an incomprehensible margin. The Big Bang started in a state of extraordinary, improbable, seemingly inexplicable order, and every attempt to explain why leads to either a regression to a prior state that faces the same problem, or an appeal to anthropic reasoning, or an appeal to a multiverse where all possible initial conditions exist, and we simply happen to be in the ordered one. None of these is satisfying. None of them resolves the mystery. The arrow of time, the thing you feel most directly in every moment of your experience, is rooted in an initial condition of the universe that has no physical explanation. There is another problem with time that has emerged more recently, and that is, in some ways, even more disorienting. Experiments in quantum mechanics have been testing the causal structure of reality, the question of whether causes must precede effects, whether the future can influence the past, whether the temporal ordering of events is as absolute as ordinary experience suggests. And the results are deeply strange. A class of experiments known as delayed choice experiments, first proposed by John Wheeler in 1978 and subsequently performed with increasing sophistication, examines what happens when a quantum particle's path, and hence its quantum nature as particle or wave, is determined after the particle has already completed most of its journey. In Wheeler's original thought experiment, you set up a double-slit apparatus but defer the decision of whether to insert a wave-detecting screen or a particle-detecting device until after the light has already passed through the slits. Wheeler asked, would the light, which had already made its decision about which slit to go through, or both slits simultaneously, before you made your experimental choice, retroactively adjust its behavior to be consistent with your later decision? And the answer, confirmed by multiple careful experiments including a 2007 experiment by a French team led by Alain Aspect, is yes. The quantum system behaves as if its past behavior is determined by the future measurement choice, not just influenced by, literally determined by. The particle that has already traveled most of its path through the apparatus somehow knows what kind of measurement is going to be made of it, and its behavior in the past is consistent with that future measurement. In a universe with an absolute, unambiguous causal arrow of time, where causes precede effects and the past is fixed, this should not be possible. And yet it keeps happening every time the experiment is run. The delayed choice experiment does not merely suggest that quantum particles have a kind of foresight. It suggests something more radical, that the distinction between past and future, at the quantum level, is not fundamental. That the causal arrow of time, that irreversible flow from cause to effect from past to future, is not built into the quantum world at the microscopic level, but emerges perhaps only when quantum systems become large enough and complex enough to exhibit the thermodynamic behavior that generates the macroscopic arrow of time. And this suggestion has been reinforced by theoretical work on a concept called quantum retrocausality, which has been developed by physicists, including Yakir Aharonov and his collaborators, into a mathematically consistent interpretation of quantum mechanics in which the quantum state of a particle is determined both by a forward-evolving wave from its preparation and a backward-evolving wave from its future measurement. This two-state vector formalism is not mainstream, but it is mathematically rigorous, makes the same predictions as standard quantum mechanics, and resolves several quantum paradoxes in a natural way, at the cost of accepting that measurement outcomes are influenced by events that have not yet happened. If the future influences the past in quantum mechanics, if causality is bidirectional at the fundamental level, then the temporal structure of reality is profoundly different from what every human being in history has assumed it to be, up until the moment when careful experiments with individual quantum particles forced the question. And speaking of the temporal structure of reality, let us take a moment with something that is not usually discussed in these terms, but that deserves to be. General relativity, Einstein's theory of gravity, treats time not as a universal absolute flow, but as a dimension of space-time that can be curved, stretched, dilated, and, in extreme cases, almost completely frozen. This is not just theoretical. GPS satellites require corrections for time dilation to function properly. Clocks run measurably slower in strong gravitational fields and at high velocities. Time is not a fixed backdrop against which events occur. It is a flexible, dynamic feature of the geometry of spacetime, affected by the distribution of mass and energy. This has been verified to extraordinary precision in countless experiments. But here is what general relativity actually implies when you follow the mathematics to its natural endpoint. At the boundary of a black hole, at the event horizon, time dilation becomes infinite. An observer watching an object fall into a black hole from the outside never sees it cross the event horizon. From the outside observer's perspective, the infalling object slows down, redshifts, fades, and asymptotically approaches the horizon without ever crossing it, frozen at the edge for the rest of eternity. but from the perspective of the object falling in, it crosses the horizon in a finite time and encounters the singularity inside. Two observers experiencing the same physical event in fundamentally different temporal frameworks, producing mutually contradictory accounts of what happens, both of which are, within their own frames, correct. General relativity demands that both perspectives are valid, and it demands that at the singularity inside a black hole, at the mathematical endpoint of gravitational collapse, the curvature of spacetime becomes infinite, the density of matter becomes infinite, and the equations that describe the universe break down completely and produce meaningless infinities, not very large numbers, actual mathematical infinities. The theory predicts its own failure. Every black hole contains at its heart a point where the equations cannot continue, where the model hits a wall that is not the wall of our ignorance, it is the wall of the formalism itself running out of road. The same breakdown occurs at the Big Bang. Work backward in time using the equations of general relativity, and the universe contracts. Galaxies approach each other, matter becomes denser, temperature climbs, and eventually you reach a point of infinite density, the initial singularity, where the equations again produce meaningless infinities, and the theory again breaks down. General relativity, the theory that has been confirmed to extraordinary precision in every observational and experimental test ever applied to it, predicts its own collapse at both the beginning of time and at the center of every black hole. These are not minor qualifications. These are places where the most successful theory of gravity ever constructed explicitly fails. And what lies beyond those failures, what actually happens at the physical reality of a singularity, what the universe was before the Big Bang, what is at the center of a black hole, is completely unknown. Not because we lack the data, though we do lack data, but because the theory that is supposed to describe it explicitly cannot. The universe has places in it where our best description of spacetime runs out, where the physics stops, where the model hits its own edge, and scientists know this, and they work around it, and they have been working around it for decades. And the resolution, a theory of quantum gravity that combines quantum mechanics and general relativity into a single coherent framework, has been the central unsolved problem of theoretical physics for most of a century. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety. Each approach has its successes and its failures. None of them has yet produced a complete, empirically tested theory. The two greatest physical theories in the history of science, quantum mechanics and general relativity, are mutually contradictory. They cannot both be exactly right, and we do not have the theory that replaces them. Let us sit with that contradiction for a moment, because it is easy to read past it without feeling its full force. Quantum mechanics and general relativity are not slightly inconsistent. They are not approximately compatible with minor corrections needed. They are fundamentally incompatible in a way that has resisted all attempts at resolution for nearly a century. Quantum mechanics describes the universe as fundamentally probabilistic, discrete, and non-local. General relativity describes the universe as fundamentally continuous, deterministic, and local, or at least locally causal. Quantum mechanics treats space and time as a fixed background stage on which quantum events occur. General relativity says space and time are themselves dynamic, curved, physical entities affected by everything that happens in them. Quantum mechanics requires that the uncertainty principle applies to all physical quantities, including the geometry of spacetime. General relativity requires that spacetime has a definite geometry at every point. When you try to apply quantum mechanics to the gravitational field, to quantize gravity the way you have quantized the electromagnetic, weak and strong forces, you get infinities that cannot be removed by any known mathematical technique. The calculation gives nonsense. And what this means is that the two theories we use to describe the universe, one governing the microscopic realm and one governing the macroscopic realm, are telling incompatible stories about what reality fundamentally is. The universe is, according to our own best theories, self-contradictory. It cannot be exactly the way both theories say it is, and yet both theories predict everything they have been asked to predict with extraordinary accuracy in their respective domains. This is the kind of situation that, if you allow yourself to really see it, has a genuinely vertiginous quality. You are not being told that some obscure corner of physics has an unresolved puzzle. You are being told that the deepest, most successful, most carefully verified theories of physical reality cannot both be correct and cannot currently be unified, and that the gap between them, the silence at the heart of theoretical physics, is the space where a complete understanding of the universe ought to be. The foundations of physics are, in a precise and non-melodramatic sense, missing. There is a level of description that should be there, that would reconcile quantum mechanics and gravity, that would explain what happens at singularities and before the Big Bang and at the Planck scale where space-time presumably becomes a foam of quantum fluctuations, and we do not have it. We have been trying to have it for nearly a century. We have built enormous accelerators, sent precision satellites into orbit, developed extraordinarily powerful mathematical tools, trained generations of brilliant minds on the problem, and the foundations remain missing. And in the absence of those foundations, all of the anomalies we have been discussing, the dark matter, the dark energy, the Hubble tension, the muon G2 anomaly, the quantum measurement problem, the quantum to classical transition, the quantum biology, are all operating in a space that lacks its deepest level of description. We are troubleshooting the upper floors of a building, while the foundation is still under construction. We cannot be certain which anomalies are hints about new particles and forces within the existing framework, and which anomalies are signs that the framework itself is wrong in ways we have not yet identified. The two categories look identical from where we are standing. Now let us go somewhere even more personal, because this story has been building outward, from quantum particles to molecules to cells to organisms to galaxies to the structure of space-time, and it is time to bring it back inward. Because the most immediate and undeniable anomaly in your experience is the fact of your own consciousness. The fact that there is something it is like to be you, reading these words, feeling the tension of accumulating uncertainty, sitting with questions that have no comfortable resolution. You are, by every measure, a physical system. You are made of atoms and molecules organized into cells, organized into organs, organized into a body that obeys every physical law that has ever been tested. The atoms in your body were forged in stars. The molecules in your brain follow the same chemistry as molecules in a test tube. The electrochemical signals that travel through your neurons are governed by the same physics as any other electrochemical process. You are, from the outside, entirely physical, and yet from the inside you are entirely experiential. There is a warmth to seeing a familiar face. There is a specific feeling to hearing a piece of music that moves you. There is a quality to the color red that is not captured by its wavelength. There is a weight to grief and a lightness to joy that exist as real things in your experience, even though they have no location, no mass, no charge, no spin, no physical property that any instrument can directly measure. The inner world of your experience is as real to you as anything in the physical world. More real in a certain sense because your access to the physical world is mediated through your experience, while your experience is direct and immediate. And yet no physical theory accounts for it, and it keeps not being accounted for year after year, decade after decade, despite enormous advances in neuroscience, cognitive science, and artificial intelligence. The hard problem of consciousness is not a young puzzle that has not yet had time to be solved. It is a puzzle that has resisted every technique, every framework, every theory that the most capable minds of the last century have brought to bear on it, and that sustained, systematic failure to explain experience in physical terms might not be an accident. It might be telling you something about the limits of the physical framework itself. The philosopher Thomas Nagel, not a mystic, not a New Age thinker, but a rigorous analytic philosopher at New York University, published a book in 2012 called Mind and Cosmos, in which he argued, carefully and with full awareness of how his argument would be received, that the standard neo-Darwinian account of life and consciousness is almost certainly wrong. Not wrong in its details, not wrong about evolution happening through natural selection, but wrong at a deeper level, because it assumes that the physical processes it describes are, in principle, sufficient to account for the existence of consciousness and the rational faculties of the mind. Nagel argued that there is no account of purely physical processes, no matter how sophisticated, no matter how complete, that explains why any physical process should be accompanied by subjective experience. His argument was not mystical. It did not appeal to any supernatural entities or forces. It was a straightforward logical point, that consciousness is not merely complex physical behavior, but something that has an inner quality that physical descriptions, by their nature, cannot capture. And therefore, he concluded, the complete story of the universe must include something that current physical science does not have room for, something about the nature of mind, about the fundamental role of experience in the structure of reality, that will require a serious expansion of our scientific worldview. The book was met with considerable hostility from the scientific mainstream, but the arguments it contained have not been refuted. They have been criticized, contextualized, and countered with alternative frameworks, none of which resolve the hard problem either. The hostility tells you something about how disturbing the implications are. You do not react with hostility to a trivial or easily dismissed argument. You react with hostility to an argument that threatens something important. And now let us pull something together that has been implicit throughout this entire narrative, something that you may have begun to sense but that deserves to be stated explicitly. All of the impossible things we have been discussing share a common structural feature. They all occur at the boundaries of measurement, at the edges of observation, at the interface between the known and the unknown. The quantum measurement problem is a problem specifically about the act of observation. The quantum to classical transition happens, or fails to happen where expected, precisely when a system is being observed or interacting with its environment in a way that generates information. The near-death experiences happen at the edge of death, at the boundary of biological function. The consciousness problem is a problem about the relationship between the external physical world and the internal experiential world, the boundary between observer and observed. The dark matter and dark energy are inferred from observations of things we cannot directly see. The wow signal came once and never repeated. It appeared at the edge of detectability and vanished. The singularities in general relativity are points where the theory breaks down at the extreme limit of its application. Every single anomaly occurs at an edge. Every impossible thing happens at a boundary. And that pattern, the location of impossibility at the edges of observation and measurement, is not random. It is either a coincidence, or it is pointing towards something about the relationship between measurement, observation, and reality that is one of the deepest features of the universe. Something that connects quantum mechanics, consciousness, cosmology, and the structure of space-time through the single thread of what it means to observe, to measure, to know. There is a concept in physics called the observer effect, and it is important to understand it precisely because it is widely misunderstood in its implications. The observer effect in quantum mechanics does not require a human being. It does not require consciousness in any specific sense. What it requires is an interaction, any physical interaction, between the quantum system and another system that records information about the first system's state. An automated detector counts as an observer in this sense. A photon bouncing off an atom and carrying away information about the atom's state counts as an observation. The physical presence of a measuring device, regardless of whether any human is watching, causes the quantum wave function to collapse. Consciousness per se is not required. This is the mainstream view, and it is important to be clear about it. But here's the part that even the mainstream view has to acknowledge. The definition of measurement, the definition of what counts as an interaction that records information and causes collapse, is itself unresolved. We know that measurement causes collapse, but we do not have a theory that tells us precisely when a physical interaction crosses the threshold from quantum unitary evolution to measurement and collapse. We know that large, complex systems appear to collapse quickly and completely due to decoherence, but we do not know what the smallest, simplest system is that counts as an observer. We do not know whether a single atom interacting with another atom constitutes a measurement. We do not know where the boundary between quantum evolution and classical observation lies. And this uncertainty about the definition of measurement, this inability to draw a crisp line between the observer and the observed, between the measuring apparatus and the system being measured, echoes the philosophical uncertainty about consciousness and its relationship to the physical world in a way that feels, increasingly, not like a coincidence. Let us introduce one more piece of evidence, one more impossible thing that keeps happening, before pulling everything together in the most unsettling way possible. This one comes from the relationship between mathematics and physical reality. Physicists have long noticed something that Eugene Wigner famously described in 1960 as the unreasonable effectiveness of mathematics. The observation is simple. Mathematical structures developed by pure mathematicians, often centuries before they had any known physical application, often developed purely for aesthetic or intellectual reasons with no reference to the physical world, keep turning out to be exactly the right language for describing physical reality. Non-Euclidean geometry, developed in the 19th century as a purely abstract mathematical exploration of what happens when you relax one of Euclid's postulates, turned out to be the mathematical framework of general relativity, the geometry of curved spacetime. Group theory, developed by Évariste Galois in the 1830s to study the abstract symmetries of polynomial equations, turned out to describe the symmetry groups of fundamental particles and form the backbone of the standard model of particle physics. Riemannian manifolds, operator algebras, fiber bundles, spinors, mathematical structures developed in abstract settings with no physical motivation, keep appearing as the natural and necessary language for describing the deepest features of physical reality. This is not what you would expect if mathematics were simply a tool that humans developed to describe observations. You would expect mathematics to describe known physical phenomena accurately, because it was developed to describe them. But pure mathematics developed in the absence of any physical application, should have no reason to be the right language for unknown physical phenomena, and yet it keeps being the right language. The universe keeps being describable by mathematical structures that mathematicians discovered by following internal aesthetic and logical criteria, completely independent of physics, which raises a question that is as old as Plato and as contemporary as the latest papers in the philosophy of mathematics. Does mathematics describe physical reality because physical reality is, at some level, mathematical? Is the universe not just described by mathematics but made of mathematics? Is the physical world an instantiation of an abstract mathematical structure, what the MIT physicist Max Tegmark calls the mathematical universe hypothesis? And if so, what does that mean for everything we think we know about the difference between the abstract and the concrete, between the ideal and the real? These are questions that can sound like philosophy dressed up as physics, and it is important to acknowledge that they are, at present, not empirically testable in any direct way. But the unreasonable effectiveness of mathematics is not a philosophical speculation. It is an observed fact about the relationship between human mathematical reasoning and physical reality, a fact that has been confirmed so consistently and across so many instances that ignoring it would be as intellectually dishonest as ignoring any other persistent pattern in the data, and it connects to the rest of the story in a way that is worth making explicit. If the universe is mathematical at its foundation, if physical reality is in some sense a mathematical structure, then the physicality of matter, the concreteness of experience, the there-ness of the world you inhabit, are all somehow properties of an abstract structure, which means that the intuition that guides our entire scientific and everyday worldview, the intuition that reality is fundamentally material, that matter is primary and everything else derives from it, may be getting the ontological hierarchy precisely backward. Not matter giving rise to abstract mathematical descriptions, but abstract mathematical structure giving rise to the appearance of matter. And if that is the case, even as a possibility worth taking seriously, then many of the anomalies we have been discussing look fundamentally different. The non-locality of entanglement is less surprising if spatial locality is not a fundamental property of the underlying structure, but an emergent feature of it. The quantum behavior of living systems is less surprising if biological systems have found ways to tap into the underlying mathematical structure more directly than classical chemistry allows. The hard problem of consciousness takes on a different character if experience is not a product of material processes, but a feature of the mathematical structure in which material processes are embedded. None of this resolves anything, but it changes the shape of the problem. It changes what impossible means. It suggests that what we have been calling impossible is not a violation of the laws of nature. It is a feature of nature that the laws we have written have not yet learned to speak. Scientists working on the leading edge of all these fields, quantum gravity, quantum information, quantum biology, consciousness science, cosmology, share something that rarely makes it into their published papers, but that comes through in conversations and interviews and informal discussions. A sense of proximity, a sense that something is about to change. A feeling that the accumulation of anomalies, the failure of incremental explanations, the convergence of impossible results across multiple independent fields is building toward something. Not a small discovery, not a new particle or a refined measurement, something structural, something conceptual. A change in the picture of what reality is, of the same magnitude as the change that produced quantum mechanics in the early 20th century, or the change that produced evolutionary biology in the 19th century, or the change that produced heliocentrism in the 16th century. Each of those revolutions, before it happened, was preceded by a period of exactly this kind of anomaly accumulation, a period when the existing framework was producing results it could not explain, when the patching and extending of the old model was becoming increasingly strained, when the people closest to the data were beginning to sense that the problem was not in the details, but in the foundations. We are in that kind of period, and the people who know the data best are among the most aware of it. There is a concept in the philosophy of science called the Duhem-Quine thesis, the observation that any individual scientific theory is not tested in isolation, but always in conjunction with a web of auxiliary assumptions, background theories, and interpretive frameworks. When an experiment produces a result that contradicts a theory, you do not have a simple refutation of that theory. You have evidence that something in the entire web, the theory or the auxiliary assumptions or the background frameworks or the interpretive choices, is wrong, but you cannot tell from the experimental result alone which element of the web is the problem. This has a profound implication for the pattern of impossible results we have been exploring, because when scientists encounter a result that contradicts their model, quantum interference in large molecules or quantum coherence in biology, or non-local correlations in entanglement experiments, or near-death experiences during zero brain activity, they always have the option of adjusting the auxiliary assumptions rather than the core theory. They can say, perhaps the molecules are actually smaller than we thought. Perhaps the quantum coherence is being generated by some mechanism we haven't identified yet. Perhaps the entanglement correlations are due to some subtle local mechanism we haven't detected. Perhaps the near-death experiences are produced by some residual brain activity that our instruments are not sensitive enough to measure. These moves are intellectually legitimate. They are part of how normal science works. But they are also how normal science can delay, sometimes for very long periods, the recognition that the core theory itself needs to change. And the history of science shows that this delay, while inevitable and in many ways healthy, ends abruptly with a revolution, when the auxiliary adjustments required to save the core theory become so numerous, so ad hoc, so inconsistent with each other, that the total weight of the patched-up model exceeds the weight of accepting that the core theory is wrong. Looking at the current state of physics, cosmology, biology, and neuroscience simultaneously, it is impossible not to notice that we are doing a great deal of patching. Dark matter is a patch. We added an invisible ingredient to the cosmological model to explain galactic rotation curves. Dark energy is a patch. We added a repulsive cosmic force to explain the accelerating expansion. The wave function collapse postulate in quantum mechanics is a patch. We added a separate, ill-defined process to explain the transition from quantum superposition to classical definite states. The various interpretations of quantum mechanics are patches, each one adding a different invisible element, parallel universes, hidden variables, relational ontologies, to make the theory tell a consistent story. The standard candle corrections in cosmological distance measurement are patches. The effective field theory approximations used when quantum mechanics and gravity would otherwise conflict are patches. The separation between classical and quantum domains that is used to avoid the contradiction between the two theories is a patch. The entire edifice of current fundamental physics is, beneath its extraordinary predictive success, a deeply patched structure, a model held together by auxiliary assumptions and approximations, and interpretive choices that are individually reasonable, but collectively beginning to strain under the weight of what the universe keeps showing us. And when you see a structure that is this extensively patched, and when the patches keep failing to contain new anomalies as they arrive, and when independent streams of data from completely separate fields of science all keep pointing toward the same region of conceptual space, toward the inadequacy of materialism, toward the non-locality of physical reality, toward the role of information and observation in the structure of the world, then you are allowed to wonder whether the patching is approaching its limit, whether the structure that lies underneath the patches once revealed will look very different from anything we currently have a name for. But here is the thing that you cannot unknow once you have seen it. The pattern is not just in the individual anomalies. The pattern is in the persistence. Every impossible thing we have discussed has survived the most rigorous attempts to eliminate it. Quantum entanglement survived Bell test after Bell test until the Nobel Committee gave up trying to be skeptical and awarded the prize. Dark matter survived decades of alternative explanations, alternative gravity theories, modifications of Newtonian dynamics, every ingenious proposal that tried to explain galactic rotation without invisible mass, and none of them worked across all the scales and contexts where dark matter's gravitational effects have been observed. The Muon G2 anomaly survived transfer from one experimental facility to another, from Brookhaven to Fermilab, where a completely rebuilt apparatus confirmed the same discrepancy. The quantum coherence in photosynthesis survived the initial wave of skepticism, the accusations of instrumental artifact, the alternative classical explanations, and emerged from that gauntlet still standing, still showing up in the data. The hard problem of consciousness survived the entire 20th century of neuroscience, cognitive science, and artificial intelligence, all of which produced extraordinary advances in our understanding of how the brain processes information, without once providing an explanation of why any physical process should be accompanied by subjective experience. These are not young anomalies that have not yet been properly examined. They are mature anomalies that have been examined extensively, from every available angle, by the best minds in the relevant fields, and they have not gone away. They have become clearer. Let us think about what it means for an anomaly to become clearer over time rather than resolving. In normal science, anomalies resolve. You find the error, fix it, and the anomaly disappears. Or you find an extension to the existing theory that accommodates the anomaly without breaking anything else, and the anomaly is absorbed. These are the two common fates of scientific anomalies, and they are what most anomalies experience most of the time. But the anomalies we have been discussing are not resolving. They are not being absorbed. They are becoming more precisely defined, more statistically significant, more clearly inconsistent with the existing framework, as the experimental and observational techniques applied to them improve. The Hubble tension is more significant now, with Planck satellite data and Hubble Space Telescope Cepheid measurements than it was 5 years ago. The quantum coherent signatures in biological systems are more clearly characterized now, with improved ultrafast spectroscopy techniques than they were in 2007. The Bell inequality violations are more decisively established now, after the loophole-free tests of 2015, than they were in 1982. Better data is making the anomalies more anomalous, not less. And this is the behavior of something real, something that is genuinely there, in the data, reflecting a genuine feature of the universe that the existing framework cannot accommodate. The fact that the anomalies become sharper and more insistent as measurement improves is the strongest possible evidence that they are not artifacts of poor measurement. They are features of reality that poor measurement was blurring. As measurement improves, the blur reduces and the feature becomes more visible. And what is becoming more visible is a universe that keeps doing things it should not be able to do. There is one more category of impossible things that we have not yet discussed, one that is perhaps the most personally immediate and the most difficult to engage with seriously in a scientific context, because the data comes from human beings rather than from instruments, and because human beings are unreliable narrators of their own experience in ways that instruments are not. But the data is too consistent, too cross-cultural, too persistent across time, and too well documented by serious researchers to simply dismiss. It is the category of anomalous cognition, the experimental evidence that some humans, under some circumstances, demonstrate awareness of information that they could not have obtained through any known sensory or inferential channel. This encompasses what the public typically calls psychic phenomena, remote viewing, precognition, telepathy, and it has the distinction of being one of the most contested areas in all of science. The reasons for the contestation are understandable. The phenomena, if real, would violate several well-established physical principles, specifically the principles of locality and causality. Information cannot travel faster than light. The future cannot influence the present. These principles are foundational to the physics we know. So any claim that humans can receive information about distant locations or future events from no known physical source is an extraordinary claim, and extraordinary claims require extraordinary evidence. The evidence that exists is not by most measures extraordinary in its individual components, but it is persistent. In the 1970s and 1980s, the United States government funded a classified research program called Stargate, which studied the potential for remote viewing, the ability of trained subjects to describe distant locations or events without any normal sensory access. The program ran for over 20 years, involved numerous experimental protocols, and produced a body of data that was reviewed at the end of the program by a panel of scientists, including statistician Jessica Utz and psychologist Ray Hyman. Utz concluded that the data showed statistical evidence of a real effect above chance, that the remote viewing sessions produced descriptions of target sites at a rate significantly higher than could be attributed to random chance. Hyman disagreed about the strength of the evidence but did not dispute that the effect was present in the data. He argued that methodological flaws in the experiments could account for it. The debate between Utz and Hyman captures the ongoing tension in this area. The effect is in the data, but its interpretation is contested. More recently, Dean Radin at the Institute of Noetic Sciences has compiled meta-analyses of controlled laboratory experiments in various areas of anomalous cognition, precognition, telepathy, mind-matter interaction, and has argued that the cumulative statistical evidence across thousands of experiments by hundreds of researchers represents a genuine effect that cannot be explained by chance or methodological error. These meta-analyses have been published in peer-reviewed journals including Frontiers in Psychology and Psychological Bulletin. They have not been retracted. They have not been definitively refuted. They sit in the scientific literature, persistent and unresolved, producing the same reaction in most scientists who encounter them: discomfort, skepticism, and a strong desire to find the methodological flaw that makes them go away. But the flaw keeps not being found to everyone's satisfaction, and the data keeps showing the same thing. Now, to be rigorous, and rigor is essential here, because this is exactly the domain where wishful thinking and motivated reasoning are most dangerous. It is important to acknowledge that the evidence for anomalous cognition is nowhere near as clean or as replicated as the evidence for quantum entanglement or dark matter. The effect sizes are small. The experimental conditions are difficult to control perfectly. The history of parapsychology is littered with cases where initial promising results collapsed under tighter experimental scrutiny. Many scientists who have examined this literature in detail remain unconvinced that a genuine anomalous effect has been demonstrated, and that skeptical position is intellectually legitimate and deserves respect. But here's the thing that makes even the skeptic's situation uncomfortable. If you apply the same standards of evidence that are applied in other areas of science, if you take a large body of independently conducted, peer-reviewed studies, pool the results in a proper meta-analysis, and calculate the probability that the observed effect could be due to chance, the anomalous cognition data passes the threshold. Not spectacularly, not with the kind of replication fidelity that quantum entanglement experiments achieve, but it passes. And the scientific community's response, which is not to engage with the meta-analyses and refute them on their own terms, but largely to ignore them, to decline to fund replication studies, to treat the entire domain as not worth serious investigation, is itself anomalous. Science as a process is supposed to follow the evidence wherever it leads, regardless of whether the destination is comfortable. The systematic avoidance of this particular territory by the mainstream scientific community is a social phenomenon, not a scientific one. And social phenomena, when they persist in the face of data, usually indicate that something important is being protected, some assumption, some worldview, some foundational commitment that the data, if taken seriously, would threaten. The assumption being protected here is the completeness of the materialist framework, the idea that all real effects have physical causes, all information transmission requires physical signals, all influences respect locality and causality. If anomalous cognition is real, even at small effect sizes, even rarely, even unreliably, then that assumption is not complete. And if that assumption is not complete, then everything built on it, the entire architecture of scientific materialism, needs to be re-examined at its foundations. You are not being asked to believe in anything supernatural. You are being asked to look at what the data shows consistently across multiple independent domains, and to sit with the possibility that the materialist framework, the assumption that physical matter governed by known physical laws is all there is, may be insufficient to describe the full range of what exists and what occurs. This is not a mystical claim, it is a scientific one. It is the same kind of claim that was made when quantum mechanics first showed that the classical mechanical framework was insufficient to describe atomic phenomena. The claim was not that physics was wrong and magic was right. The claim was that the framework needed to expand, that there were features of reality that the existing framework could not accommodate, and that a broader framework was needed. Quantum mechanics was that broader framework at the atomic scale. What we may be approaching now is a broader framework at a deeper scale, one that accommodates not just the quantum behavior of matter, but the relationship between matter and information, between physical processes and experience, between the local and the non-local, between the temporal and the atemporal, a framework that does not discard what we know, but that contextualizes it within a richer description of what is real. And every impossible thing we have been discussing, every anomaly, every persistent result that should not be there, every signal that survives every attempt to eliminate it, is a clue about what that broader framework must contain. Let us talk about something called retrocausality in biology, because it connects the quantum biology findings to the temporal anomalies in quantum mechanics in a way that is deeply strange and deeply interesting. Some researchers in the field of quantum biology have been exploring the possibility that quantum effects in biological systems are not just a matter of quantum coherence or quantum tunneling, the quantum phenomena that are relatively well established in biology, but might involve something more radical, a kind of quantum retrocausality, where the outcome of a biological process influences the quantum states that give rise to it, in a way that involves backward-in-time causal connections. This is, to put it mildly, a controversial idea, but it connects to something that has been observed in quantum systems more broadly, that certain quantum processes, particularly those involving measurement and entanglement, seem to exhibit correlations between spatially and temporally separated events that cannot be explained by any forward causal, local mechanism. If quantum biology is exploiting not just quantum coherence but quantum temporal non-locality, if living systems have evolved to use the backward-in-time causal connections that quantum mechanics permits, then the efficiency of biological processes like enzyme catalysis, which operate at rates that classical activation energy barriers should prevent, has an explanation that is stranger than anyone had anticipated. Life is not just using quantum mechanics. Life might be using the aspects of quantum mechanics that are most deeply incompatible with our ordinary sense of causality and time, and evolution, the blind, undirected process of natural selection, acting on random variation over billions of years, might have stumbled onto features of physical reality that our conscious, intentional science has only recently discovered. The universe built quantum temporal connections into the machinery of life long before anyone had a theory to describe them. This thought, that evolution might have discovered features of quantum reality before science did, opens a perspective that is worth dwelling on. Evolution has no mind, it has no agenda, it has no access to theory. It simply selects for whatever works, whatever produces organisms that survive and reproduce, regardless of whether the mechanism it stumbles upon makes sense within any given theoretical framework. And evolution has been running for approximately 4 billion years on this planet, selecting across an unimaginably vast number of organisms and biochemical systems for the most efficient solutions to the problems of survival and reproduction. If quantum effects in biology are real, if evolution has harnessed quantum coherence, quantum tunneling, quantum entanglement, and possibly quantum retrocausality in the biochemical machinery of life, then nature itself is a kind of experimental program that has been testing the properties of physical reality at the quantum biological interface for 4 billion years. And the results of that program, the biochemistry of photosynthesis, enzyme catalysis, bird navigation, and possibly olfaction, are now showing up in our labs as anomalies, as impossible results, as things that should not work the way they do. But they have been working that way for billions of years. Nature found the solution long before we found the problem. And the problem is that our framework for what is possible has been too narrow all along. Life has been operating outside that framework, quietly, persistently, for the entirety of its existence on this planet. And only now, with our most sophisticated instruments and our most careful experimental methods, are we beginning to see the edges of what it has been doing. Here is something that follows directly from that observation, and that rarely gets stated explicitly in these discussions. If living systems have been exploiting quantum effects at biological scales, scales where quantum effects were assumed to be irrelevant, then the assumption of the irrelevance of quantum effects at those scales was not a minor error. It was a fundamental mistake in how we divided the physical world into domains. The division between quantum and classical, between microscopic and macroscopic, between the world of wave functions and the world of solid objects, has been one of the organizing principles of 20th century science. It is what made quantum mechanics a special topic, a strange and restricted domain, important for atoms and transistors but not for organisms and ecosystems and brains. If that division is wrong, if quantum effects are not confined to the microscopic domain, but permeate the biological world as well, then the implications extend far beyond photosynthesis and enzyme catalysis. They extend to the brain, to the neural processes that generate thought and memory and perception and ultimately consciousness. The brain is a warm, wet, noisy environment, and for decades neuroscientists have assumed on that basis that quantum effects play no significant role in cognition. But the same argument was made about photosynthesis: warm, wet, noisy, and it was wrong. And now the question that Roger Penrose and Stuart Hameroff have been raising since the 1990s, with their orchestrated objective reduction theory of consciousness, which proposes that quantum processes in microtubules inside neurons play a role in generating conscious experience, cannot be as easily dismissed as it was when first proposed. Not because the theory has been proven, it has not, and it faces serious challenges, but because the assumption that quantum effects are irrelevant to biological systems at the neural scale has been eroded by everything quantum biology has subsequently found. The theoretical landscape has shifted, And in a shifted theoretical landscape, ideas that previously seemed impossible become merely unproven, and the unproven keeps accumulating. Let us talk about the anomalous results in placebo research, an area that most people file under psychology, but that, looked at carefully, raises questions about the relationship between mind and matter that are as fundamental as anything in quantum mechanics. The placebo effect is well known. Give someone a sugar pill and tell them it is an active medication, and in many cases they will experience real physiological improvement, measurable reduction in pain, measurable changes in blood chemistry, measurable improvement in symptoms of depression, Parkinson's disease, irritable bowel syndrome, and numerous other conditions. This has been known and studied for decades, and the standard explanation is that the placebo triggers real physiological changes through the mind-body connection, through the activation of the immune system, the release of endorphins, the modulation of the autonomic nervous system, all driven by the patient's expectation and belief. This is a physically acceptable explanation. It invokes known biological mechanisms, even if they are incompletely understood. But there are aspects of placebo research that push beyond this comfortable explanation. There are studies showing that open-label placebos that patients are told explicitly are placebos, still produce significant therapeutic effects. There are studies showing that the quality of the clinical interaction, the warmth and attention of the physician, produces measurable physiological changes independently of any medication. There are studies showing that the same active medication has different effects depending on what the patient believes about it. Different analgesic potency, different side effect profiles, different neural activation patterns, purely as a function of the information the patient has been given about the drug. These results are not anomalous in a framework that accepts a rich, bidirectional relationship between mental states and physical processes. They are anomalous in a framework that treats the body as a purely physical mechanism and the mind as an epiphenomenon, a byproduct of physical processes with no causal power over those processes. Because if the mind is merely a byproduct of physical brain processes without any independent causal power, then what a patient believes about their medication should have no effect on the physiological action of that medication. Belief is a mental state. If mental states have no causal power over physical processes, belief cannot change the analgesic potency of a drug, and yet it does, reproducibly, significantly, across independent studies. The data on placebo effects and the nocebo effect, the inverse, where negative expectations produce negative physiological outcomes, collectively constitute a large and well-replicated body of evidence that mental states have direct causal power over physical biological processes, not mediated by behavior, not because the patient does something differently as a result of their belief, but directly through mechanisms that involve the central nervous system modulating immune function, pain processing, and physiological response. The mind is doing something to the body that pure epiphenomenalism cannot account for, and if the mind has causal power over biological processes, then the question of what the mind is and how it relates to the physical systems it influences is not just a philosophical question. It is a question about the causal structure of the physical world. It is a question about how reality works. By this point in the story, something has been building beneath the surface of each individual observation, each impossible result, each anomaly that refuses to go away. And it is time to name it, not as a conclusion but as the pattern itself, because the pattern is what this entire story is about. The pattern is this: the universe is consistently producing results that point beyond its own official description, not occasionally, not in one domain, not attributable to error or artifact or insufficiently sophisticated measurement. Consistently, persistently, across the full range of scales from subatomic to cosmological, across the full range of disciplines from physics to biology to neuroscience, across the full range of investigative methods from laboratory experiment to astronomical observation to clinical study. The universe keeps showing us things that its own current description says cannot be there. Quantum systems that transcend the quantum to classical boundary. Dark ingredients that constitute 95% of everything. Non-local correlations between distant particles. Quantum effects in living cells. Consciousness that persists at the edge of biological death. Mental states that have causal power over physical processes. Mathematical structures that describe physical reality before they are asked to. Temporal correlations that run backward through time. Signals from the cosmos that have no known source. These are not random anomalies scattered across an otherwise coherent picture. They are connected. They share a structure. They all point toward the same direction. toward a universe that is deeper, more connected, more information-rich, more experiential, and more strange than the framework we have been using to describe it allows. The question that this pattern demands is not which anomaly is most important, or which experiment needs to be replicated most urgently. The question it demands is more fundamental. What kind of universe would produce this pattern? What properties would a universe need to have in order to generate, across every domain and every scale, results that consistently exceed the capacity of a materialist, local, causally linear framework to explain? And when you ask that question honestly, a set of properties begins to emerge. A universe in which information is more fundamental than matter. A universe in which locality is emergent rather than fundamental. A universe in which consciousness is not a byproduct of physical complexity, but a feature of the substrate in which physical complexity is embedded. A universe in which time is not a one-way street, but a dimension with a more complex topology than our ordinary experience suggests. A universe in which the boundary between observer and observed is not sharp, not absolute, but context-dependent and dynamic. A universe in which what we call the laws of physics are not the deepest description of reality, but an effective description, accurate within a certain domain, the way Newtonian mechanics is accurate within a certain domain, of something more fundamental that we have not yet identified. This is not a mystical description. It is a scientific description of the properties that the data is pointing toward. It is what the evidence, taken seriously, taken in aggregate, taken across all its domains, is saying about what kind of reality we inhabit. And there is something important about the timing of this realization. We are living in the most technologically powerful period in human history. We have instruments of extraordinary sensitivity, particle accelerators that probe the structure of matter at scales far smaller than anything accessible a century ago, telescopes that observe light from the edge of the observable universe, quantum computers that can maintain and manipulate quantum superpositions in ways that were impossible even 20 years ago, brain imaging technologies that can watch individual neurons fire, computational tools that can process data sets of a size and complexity that no previous generation of scientists could have approached. We have more data, better instruments, more powerful analytical tools, and more highly trained researchers than at any previous point in human history. And we are producing more anomalies than ever. The anomalies are not a product of primitive methods that will improve away. They are a product of our most sophisticated methods, finding things that our most sophisticated models cannot explain. The technology is working. The physics is struggling. The biology is working. The cosmology is struggling. The neuroscience is working. The philosophy of mind is struggling. The improvement in instruments has not brought the anomalies under control. It has brought them into sharper relief. It has made them more insistent, more precise, more clearly anomalous. And that is what tells you, more than anything else, that you are not dealing with measurement error. You are dealing with measurement discovery. You have been with this story for a long time now, and you have accumulated something. Not a conclusion. There is no conclusion available. Not yet, perhaps not, for a very long time. But a weight, a feeling for the shape of something that is too large to see directly, but whose outline can be traced through the accumulation of everything we have been through together. And what that outline describes is not comforting in the way that scientific progress is usually comforting, not the comfort of a solved problem, a confirmed theory, a resolved mystery. It is the other kind of comfort, rarer and stranger, the comfort of finally being allowed to see the problem clearly, of finally stopping pretending that the anomalies are flukes, that the impossible results are errors, that the framework is intact and needs only minor repairs, of finally acknowledging openly and without apology that the universe is consistently producing results that the universe's own official description says it cannot produce, and that this is not a new problem. It has been building for a century. It has been building since the first double-slit experiment with electrons showed that particles were waves, since the first measurements of galactic rotation showed that galaxies contained invisible mass, since the first near-death experience was documented with medical rigor, since the first Bell test showed that locality was not a feature of fundamental reality. The impossible results are not new. What is new is the accumulation. What is new is the pattern. What is new is the realization, which comes slowly and then all at once, that this is not a series of separate puzzles awaiting separate solutions. This is a single, coherent, persistent signal from the universe about its own nature, a signal that our current framework is not equipped to decode, a signal that something is here, something is real, something is happening, something that our most powerful theories and our most sensitive instruments keep detecting without being able to explain. And the signal keeps coming through. Every time we run the experiment, every time we look at the data, every time we push the instruments a little further, cool them a little lower, isolate the system a little more completely, the signal is there, clearer than before, more insistent than before, more impossible than before, and it does not resolve. It does not simplify. It does not collapse into something comfortable and known. It stays. It persists. It recurs, like something knocking from the other side of a wall, patient, consistent, and completely certain that you are starting to hear it. Think about what entanglement actually means when you sit with it long enough. Two particles share a quantum state. They are separated, sent in opposite directions, placed on opposite sides of the planet, in principle placed on opposite sides of the galaxy, because the physics makes no specification about distance. When you measure one, the other instantly assumes a correlated state. Instantly, not after a delay proportional to the distance, not after a signal travels between them at the speed of light. Instantly, regardless of distance. This does not allow you to send information faster than light, because the measurement outcomes are random. You cannot control what result you get when you measure one particle, and so you cannot use the correlation to send a message. The no communication theorem is valid. The impossibility of faster-than-light information transmission is preserved. But something is connected across arbitrary distances in a way that has no spatial structure. The correlation exists and is real. It has been measured. It has won a Nobel Prize. And it has no physical mechanism. There is no field that propagates between the particles. There is no signal. There is no carrier. There is nothing in the space between them that accounts for the correlation. The particles are correlated across distance, without anything connecting them through that distance, which means that the space between them, the physical space that you assume separates all things from all other things, is, for this correlation, not doing what space is supposed to do. Space is supposed to separate. Space is supposed to mean that distant things are independent, that what happens here does not instantly affect what happens there without some signal traveling the intervening distance. But for entangled particles, space does not do this. The spatial separation is real in the sense that you cannot exploit the correlation to send information faster than light. But the separation does not prevent the correlation from being instantaneous and complete. Space, in this case, is not the fundamental separator it appears to be. And if space is not always a fundamental separator, if there are relationships between parts of reality that do not respect the spatial structure that appears to govern everything else, then the nature of space itself is different from what it seems. Space might not be what it appears to be. It might be a feature of the physical world that emerges from something deeper that has no spatial structure at all, something that is, at its fundamental level, entirely undivided. And if space might not be fundamental, what about the matter that occupies it? What about the particles, the electrons, quarks, photons, neutrinos, that the Standard Model describes as the fundamental building blocks of physical reality? Because there is something about those particles, when you look at them closely enough, that is deeply strange in a way that goes beyond the quantum weirdness we have already discussed. These particles are not tiny objects. They are not miniature spheres or pebbles or specks of something. When physicists say that an electron is a point particle, they mean something more radical than it sounds. They mean that the electron has no measurable size. Its cross-section in scattering experiments is consistent with a geometrical point, an object with no spatial extent whatsoever. And yet it has mass, charge, and spin, physical properties that in classical physics would require a physical object to have spatial extent in order to possess them. A classical spinning object requires a physical structure that can rotate. An electron has spin, it has angular momentum, but it is not rotating because there is no physical structure that could rotate. Electron spin is an intrinsic property of the particle that has no classical analog, no spatial mechanism, no underlying rotational structure. It is spin without anything spinning. It is angular momentum without rotation. It is a property that exists without a physical structure to instantiate it. What the electron actually is, what it is made of, what gives it its properties in the absence of any physical structure, is not known. It is described perfectly by the mathematics of quantum field theory, but the description is mathematical, not physical. It tells you what the electron does, not what the electron is, and the question of what it is remains, when examined carefully, completely open. The same is true of every fundamental particle. The quarks inside a proton are bound together by the strong force, carried by particles called gluons. But the strong force has a property called color confinement. which means that quarks cannot exist in isolation. They are always found in bound states, always accompanied by other quarks or antiquarks, never observable alone. No individual quark has ever been directly observed. What we observe are the composite particles they form: protons, neutrons, mesons. We infer the quarks from the behavior of these composites. We have overwhelming evidence for their existence, but we have never seen one. The most fundamental constituents of all ordinary matter are permanently hidden from direct observation by the physics of the force that binds them. And the quarks themselves, what are they? They are also described as point particles in the Standard Model. They also have no spatial extent, no internal structure, no underlying physical object that the mathematical description maps onto. They are like the electron, mathematical entities described with extraordinary precision, instantiated in physical reality in ways we cannot fully visualize, made of nothing that has an intuitive physical description. The solid world you inhabit, the table, the chair, the ground beneath your feet, is made of atoms. The atoms are made of nuclei and electrons. The nuclei are made of protons and neutrons. The protons and neutrons are made of quarks. And the quarks, the final layer, are mathematical objects with no physical substrate. The solidity of the world rests on a foundation of pure mathematical abstraction, and that, when you sit with it long enough, starts to feel less like a description of reality and more like a description of a description, a model of something whose ultimate nature the model cannot reach. Now come with me to a specific experiment, one that was performed first in the early 2000s and has been repeated and refined many times since, that demonstrates the pattern we have been building toward in perhaps the most visceral and immediate way. It is a test of macroscopic quantum superposition, and it was performed using a device called a superconducting quantum interference device, or SQUID. A SQUID is a tiny loop of superconducting wire that carries electrical current. In 2000, Jonathan Friedman and colleagues at Stony Brook University, and separately Caspar van der Waal and colleagues at Delft University, prepared SQUIDs in a state of quantum superposition, not a superposition of atomic-scale particles, a superposition of macroscopic states, states involving trillions of electrons flowing simultaneously in opposite directions around the same loop. Two macroscopic electrical currents, each consisting of trillions of electrons, flowing in both directions around the loop at the same time. Not one current that we haven't measured yet, not a current whose direction we are uncertain about, but a genuinely quantum superposed state in which both macroscopic current directions exist simultaneously, until measured, at which point the superposition collapses into one definite direction. This is not a thought experiment. It happened. Trillions of electrons, a macroscopic amount of matter by quantum standards, existed in two macroscopic states simultaneously. The quantum world was not staying at the atomic scale. It was asserting itself at the scale of things you could theoretically detect with an oscilloscope. The Schrödinger's cat that is supposed to be a thought experiment illustrating the absurdity of quantum superposition applied to macroscopic objects, the experiment that was designed to show why quantum mechanics cannot apply to large-scale objects, has been approximated in reality, not with a cat, but with currents of electrons that are macroscopic by every relevant measure. And every time this experiment is run, under sufficiently controlled conditions, the quantum superposition is confirmed. Schrödinger designed his cat thought experiment as a reductio ad absurdum, as a demonstration that quantum mechanics, if applied naively to large objects, produce conclusions so absurd that the theory must be misunderstood or incomplete. The cat in the box, linked to a quantum event, should be in a superposition of alive and dead states until the box is opened. This is absurd, Schrödinger said. Cats are either alive or dead. Therefore, something in the quantum description must be wrong when applied at this scale. And for most of the 20th century, the physics community more or less agreed, not that the quantum description was wrong, but that it did not apply to macroscopic objects in the naive way the thought experiment suggested. Decoherence explained why. Macroscopic objects interact with too many environmental particles too rapidly for quantum superpositions to survive. The SQUID experiments push back against this comfortable resolution. They do not demonstrate a superposed cat, but they demonstrate superposed macroscopic currents. They demonstrate that the principle of quantum superposition applies to states involving numbers of particles far larger than the quantum scale is supposed to accommodate, as long as the system can be sufficiently isolated from environmental interaction. And as isolation techniques improve, as cryogenic cooling approaches absolute zero more closely, as magnetic and electromagnetic shielding becomes more complete, as vibration isolation and vacuum technology advances, The experiments keep pushing the boundary. The boundary keeps moving. The quantum world keeps asserting itself at larger and larger scales. And the question that keeps asserting itself alongside it, at what scale does it stop, keeps failing to find an answer in the experimental data. There is a concept developed by the physicist David Bohm, a student of Einstein and one of the most original and controversial physicists of the 20th century, that provides a framework for thinking about everything we have been discussing, not as a collection of separate anomalies, but as manifestations of a single underlying feature of reality. Bohm called it the implicate order, the idea that the apparent separateness and locality of the physical world we observe is a kind of unfolded projection, an explicate order of a deeper reality in which everything is fundamentally enfolded together, in which the separation between particles, between regions of space, between past and future, is not a fundamental feature of what exists, but a feature of how the underlying wholeness is expressed at the level of ordinary experience. Bohm developed this idea in detail in his 1980 book, Wholeness and the Implicate Order, and he argued that it provided a natural explanation for quantum non-locality, for the apparent paradoxes of quantum mechanics, and for a range of other phenomena that the standard interpretation struggled to accommodate. The implicate order is not just a philosophical metaphor. It was developed by Bohm as a serious physical proposal, connected to his pilot wave interpretation of quantum mechanics, also known as Bohmian mechanics, which is a mathematically rigorous alternative to the Copenhagen interpretation that describes every particle as having a definite position at all times, guided by a pilot wave that responds instantaneously to the entire experimental configuration. In Bohmian mechanics, the non-locality of entanglement is not a paradox. It is a direct expression of the fact that the universe is, at the level of the pilot wave, an undivided whole in which every part responds to every other part instantly, regardless of distance. Bohmian mechanics makes exactly the same experimental predictions as standard quantum mechanics. It has never been refuted experimentally, and it tells a completely different story about what is really happening, a story in which particles are real and definite, trajectories are real and precise, and the apparent randomness of quantum measurement outcomes is not fundamental indeterminism, but the result of our incomplete knowledge of the initial conditions. The quantum weirdness is not in the particles, it is in the pilot wave, in the underlying wholeness of the universe that guides the particles, and that manifests the correlations we observe. The universe is, in Bohm's picture, profoundly whole. The apparent separateness of things is the surface, the connection is the depth, and the anomalies, the non-local entanglement, the wave-particle duality, the interference of single particles with themselves, the collapse of superpositions upon measurement, are all, in this picture, expressions of the wholeness asserting itself at the surface level of the explicate order, not violations of the laws of nature, manifestations of the deepest law of nature, that beneath the apparent multiplicity and separateness of the physical world, everything is one. This is not mysticism. This is a rigorous physical interpretation developed by a serious physicist that is fully consistent with all available experimental data. It simply requires accepting something that our intuition resists with extraordinary force, that the separateness of things is not fundamental, that the world is not made of separate pieces, that it is made of one thing, expressing itself in many forms, always connected at a level too deep for the surface picture to reveal. Bohm's framework has never been adopted by the mainstream physics community as the preferred interpretation of quantum mechanics. It has been criticized on various grounds. It requires non-locality, which many physicists find deeply uncomfortable, even though non-locality has been experimentally confirmed. It has been extended to relativistic quantum field theory only with significant difficulty. It is sometimes criticized for being empirically equivalent to the standard interpretation while being ontologically more extravagant. But the resistance to Bohmian mechanics, like the resistance to taking anomalous cognition seriously, like the resistance to taking the hard problem of consciousness seriously, is not purely scientific. It is partly a matter of what the scientific community is willing to accept as an ontological framework, what picture of reality it is willing to entertain. And the picture that Bohm's framework offers, a fundamentally whole, non-local, deeply interconnected universe in which apparent separateness is a surface phenomenon, is a picture that does not fit comfortably with the materialist, atomistic, locally causal worldview that underlies most of 20th century science. It requires giving up something that scientists and non-scientists alike hold very dear, the intuition that things are separate, that distance means independence, that the world is made of distinct parts that influence each other only through local contact. That intuition feels like common sense, it feels like a fact. And the data, from Bell tests, from the double slit, from entanglement experiments of every kind, from the very structure of quantum mechanics itself, says that it is not a fact. It is an assumption, and it is wrong. Now imagine for a moment what science looks like if that assumption is wrong. If the universe is fundamentally whole, fundamentally non-local, fundamentally connected at a level below the appearance of separateness, if the implicate order is real, then the methodology of science, which is built on the isolation and analysis of separate parts, is a methodology that is systematically biased toward describing the explicate order while remaining blind to the implicate. Science has been extraordinarily successful at mapping the surface. It has built the most accurate descriptions of the behavior of physical systems that human intelligence has ever achieved. But if the surface is not all there is, if there is a depth that the methodology of separating and isolating and measuring parts simply cannot access, then the limits of science are not just about what we have not yet measured. They are about what the measurement process itself cannot reach, not because of technological limitations that future instruments will overcome, but because the act of isolating a system from its environment, controlling variables, eliminating confounding factors, the act of doing science, is precisely the act of removing the object of study from the wholeness that, if Bohm is right, is where the most important features of reality reside. The anomalies we have been discussing, the quantum effects that appear when systems are isolated, the entanglement correlations that survive any distance, the quantum coherence in living systems, the non-local connections between mind and matter suggested by placebo research and anomalous cognition data, might all be glimpses of the implicate order asserting itself through the gaps in our isolating methodology. Moments when the wholeness peeks through. Moments when the depth of the universe makes itself briefly visible at the surface. And this brings us to something that is as close to the heart of this entire story as it is possible to get. Something that requires sitting with very carefully, without rushing to a conclusion in either direction. The question of whether the universe is fundamentally mindless, or whether mind, experience, awareness, subjectivity, is somehow woven into the fabric of what exists at the deepest level. This is the question of panpsychism, and it has been making a quiet but significant comeback in academic philosophy and increasingly in the physics community. Panpsychism is the view that experiential or proto-experiential properties are fundamental features of reality, not produced by physical complexity at the level of neurons or organisms, but present at every level of physical organization, all the way down to the most fundamental constituents of matter. Not that electrons are conscious in the way that you are conscious, but that there is something, however faint and simple, that it is like to be an electron, some minimal experiential property that, when organized into the extraordinary complexity of a human brain, gives rise to the richly textured inner life you experience as your own. Panpsychism sounds bizarre from within the materialist framework. It sounds like the kind of idea that would appeal to someone who had not thought carefully enough about the hard problem of consciousness. But the hard problem of consciousness is precisely why some of the most careful thinkers about the nature of mind have arrived at panpsychism. Not as a mystical refuge, but as the most logically consistent response to a specific argumentative challenge. If you cannot derive experience from any physical process that lacks experience, if experience is not reducible to information processing, not reducible to neural firing patterns, not reducible to any physical description, however detailed, then either experience is a fundamental feature of reality, present at all levels, or it emerges from nothing at some threshold of physical complexity, in a way that is entirely mysterious and inexplicable. Panpsychism says, the first option is more scientifically respectable than the second, because science, as a general principle, prefers to explain the complex in terms of the simple, rather than to invoke unexplained emergence from nothing. Ism that engage seriously with the objections and work through the implications with precision and honesty. Goff in particular has been a visible and careful advocate for what he calls cosmopsychism, a version of the view in which the universe as a whole is the fundamental experiential entity, and individual minds are not additions of experience to a mindless universe but rather partial aspects of a universal experiential reality. This is a view with deep roots in the history of philosophy, from Spinoza's monism to Schopenhauer's will to Whitehead's process philosophy. But Goff's version is formulated in direct engagement with contemporary physics and neuroscience. taking seriously the scientific data while arguing that no purely physical theory can account for it. The resistance to panpsychism in mainstream scientific circles is intense and understandable. It feels like a regression, like abandoning the hard-won clarity of scientific materialism for something uncomfortably close to animism or mysticism. But the resistance itself is worth examining, because the argument against panpsychism is not usually that it has been refuted by evidence. It is usually that it is counterintuitive, that it feels wrong, that it is not the kind of thing that serious scientists should be entertaining. And those are social and psychological reasons, not scientific ones. The evidence, the persistent failure to explain consciousness in purely physical terms, the anomalous results at the quantum consciousness interface, the data on near-death experiences and placebo effects and anomalous cognition does not decisively confirm panpsychism, but it does not refute it. And the sustained failure of every alternative to make progress on the hard problem suggests that the direction panpsychism is pointing, toward experience as a fundamental rather than emergent feature of reality, deserves more serious engagement than it typically receives. Let us come back to the physical universe one more time, because there is one more impossible thing that needs to be named, one more anomaly that sits at the intersection of physics and philosophy in a way that illuminates everything else we have discussed. It is the fine-tuning problem. The fundamental constants of nature, the speed of light, the gravitational constant, the mass of the electron, the charge of the proton, the strength of the strong nuclear force, the cosmological constant, and dozens of others, have specific values that are necessary for the universe to contain stars, planets, atoms, and life. If any of these constants were slightly different, in many cases different by an extraordinarily small margin, the universe would be radically inhospitable to the kind of complexity that life requires. If the cosmological constant were slightly larger, the universe would have expanded so rapidly after the Big Bang that matter would never have clumped together into galaxies and stars. If it were slightly smaller in the negative direction, the universe would have collapsed back in on itself before stars could form. The observed value of the cosmological constant is extraordinarily close to zero, but not exactly zero, and the value required for a life-permitting universe sits in a range that is, by naive probabilistic reasoning, almost incomprehensibly narrow. Physicist Leonard Susskind has estimated that the fine-tuning of the cosmological constant represents a 1 in 10 to the power of 120 precision, a number so specific that if you were to choose it randomly from the space of all possible values, you would be incomparably less likely to land on it than you would be to randomly select a specific atom from among all the atoms in the observable universe. And the cosmological constant is not the only fine-tuned parameter. The ratio of the electromagnetic force to the gravitational force must fall within a narrow range for stars to be stable. The masses of the up quark and down quark must be close enough to each other that stable protons and neutrons can form, but different enough that protons do not decay too rapidly. The strong nuclear force must be strong enough to bind atomic nuclei together, but not so strong that all hydrogen is converted into helium in the early universe, eliminating the fuel for stars and the hydrogen necessary for water. The list goes on, and the collective fine-tuning of all the fundamental constants when considered together represents a degree of specificity that has no natural explanation within the current physical framework. Scientists have proposed two main responses to the fine-tuning problem. The first is the anthropic principle. We observe these values because they are the values compatible with the existence of observers. If the constants were different, there would be no one to observe them. This is logically valid but scientifically unsatisfying. It tells you why you would observe life-permitting values if you exist to observe anything, but it does not tell you why life-permitting values exist at all. The second response is the multiverse. There are an enormous number of universes, each with different values of the fundamental constants, and we happen to exist in one where the values permit life. This transforms the fine-tuning from a mystery into a selection effect. Of course, we are in a life-permitting universe because all the others lack observers. But the multiverse, while it is taken seriously by many physicists, is itself an assumption. There is no direct evidence for other universes, and the hypothesis is not currently testable by any known method. It resolves one mystery by invoking another. Why are there many universes with varying constants? What generates them? What is the mechanism? The explanation requires its own explanation, and that explanation requires its own, in a regression that has no obvious end. There is a third response to the fine-tuning problem that almost no physicist is willing to state in a professional context. but that several have gestured toward in books written for general audiences, in late-night conversations at conferences, in the kind of speculation that happens when the tape recorder is off. The third response is, the universe was designed, not necessarily in a theological sense, not necessarily by a personal God with intentions and preferences, but in the more general sense that the specific values of the fundamental constants reflect choices made by some kind of agency at a level of reality that physics currently has no language for. This idea connects to the simulation hypothesis. Perhaps the constants were set by whatever process generated the simulation. It connects to panpsychism. Perhaps the universe's experiential nature at the most fundamental level includes some form of self-organization or teleological bias toward complexity and life. It connects to the mathematical universe hypothesis. Perhaps the specific mathematical structure that instantiates as our physical reality was selected from among all possible mathematical structures by some criterion that favors life and mind. None of these formulations are rigorous. None of them are testable in any currently conceivable way. But the fine-tuning data is rigorous and testable, and it persists and resists comfortable explanation. And the history of science is full of moments when a result that seemed to demand an uncomfortable conclusion turned out eventually to demand exactly that conclusion. Not because the scientists were forced to it by sentiment or faith, but because every alternative explanation failed, and the uncomfortable conclusion was the only one left standing. There is a way in which the accumulation of impossible results we have been traversing begins to feel, at some point in the journey, like a different kind of discovery than any individual result could be. Each individual anomaly, the quantum interference, the dark matter, the Hubble tension, the quantum coherence in biology, the near-death experiences, the fine-tuning, is a specific, bounded, empirical puzzle. But the pattern of their accumulation, the fact that they keep appearing, keep surviving scrutiny, keep pointing in the same direction, across every domain and every scale, is a discovery of a different kind. It is a discovery about the nature of the scientific project itself, about what the scientific project, followed with sufficient rigor and sufficient honesty, eventually encounters. What it encounters at the edges of every domain, at the limits of every measurement, at the boundaries of every framework, is the same thing: a universe that is more than the framework can contain, more connected than locality allows, more informed than matter alone explains, more experiential than physical processes account for, more precisely configured than chance permits, more strange than the comfortable picture allows. And this repeated encounter with the more, this systematic discovery, across all fields, that the universe is more than the current model describes, is not a failure of science. It is science working as it is supposed to work. It is science following the evidence to the edge of what it currently understands, and finding, with increasing clarity, that the edge is real, and that beyond it, there is something. The nature of that something is not yet known, but its existence and its persistent anomaly-generating, impossible result-producing existence is one of the most well-supported conclusions in the history of scientific investigation. You are someone who has now spent considerable time with this material. You have moved through quantum mechanics and cosmology and biology and neuroscience and philosophy and the nature of consciousness and the fine-tuning of the constants. You have encountered in each domain results that should not be possible, that have survived every attempt to eliminate them, that point consistently toward a universe that exceeds its own description. And somewhere in that journey, perhaps early, perhaps late, perhaps only now, something shifted in the way the impossibility feels. At first, each impossible result felt like an isolated puzzle, a specific problem in a specific domain waiting for a specific solution. The double slit experiment is weird, but it is a quantum weirdness, and quantum weirdness is expected. Dark matter is puzzling, but it is a cosmological puzzle, and cosmology has puzzles. The hard problem of consciousness is hard, but philosophy has always had hard problems. Each anomaly encountered alone can be held at arm's length. It can be categorized as someone else's problem, in someone else's domain, waiting for someone else's solution. But as the anomalies accumulate, as you see them appearing in domain after domain, resisting solution after solution, pointing in the same direction again and again, the arm's length becomes harder to maintain, because the pattern is not in any single domain. The pattern is across all of them. And a pattern across all domains is not a domain-specific problem waiting for a domain-specific solution. It is a foundational problem, a problem with the foundation. And what does it feel like to recognize that the foundation has a problem? Not the comfortable feeling of an unsolved puzzle. Puzzles feel solvable, finite, contained, not the exciting feeling of a new discovery. Discoveries feel like gains, like additions to what you know. It feels like something subtler and less comfortable than either of those. It feels like standing in a room you have lived in your entire life and noticing, for the first time, that one of the walls is not solid, that you had assumed it was solid. It looked solid, it sounded solid when you knocked on it. Every piece of evidence available to your ordinary senses confirmed that it was solid. And then, with the right instrument, at the right frequency, with the right sensitivity, you find that it is not, that behind it there is something that the room's architect did not put on any blueprint, something that has been there the whole time, behind the apparently solid surface, generating strange sounds that you had been attributing to the pipes, producing faint effects that you had been dismissing as drafts, making the instruments behave in ways you had been explaining away as calibration errors. The wall is not solid, something is behind it, and you cannot unknow this. Once you have seen the instruments respond, once you have recognized the pattern, once you have traced the anomalies back to the same source, you cannot go back to treating the wall as solid. You cannot go back to living in the room as if it is all there is, not because you know what is on the other side, but because you know the wall is not what it appeared to be, and that knowledge changes everything about how the room feels. This is where many people, scientists and non-scientists alike, want the story to resolve. They want the next sentence to be, and here is what is on the other side. Here is the new framework. Here is the theory that explains everything. Here is the resolution of all the anomalies, the answer to all the impossible results, the picture of reality that accommodates everything the current model cannot, and it would be dishonest to pretend that this resolution exists. It does not. Not yet. Perhaps not for a very long time. The physicists working on quantum gravity do not have a complete theory. The cosmologists studying dark energy do not know what it is. The neuroscientists working on consciousness do not have a solution to the hard problem. The quantum biologists studying coherence in living systems do not fully understand how or why it persists. The parapsychologists documenting anomalous cognition do not have a mechanism. The philosophers of mind who have moved toward panpsychism do not have a way to test it. Every field is at the edge of what it currently knows, and the edge is real, and there is no map of what lies beyond it. The honest position, the scientifically rigorous, intellectually courageous, epistemically responsible position, is to acknowledge this, to say, we do not know, we have found the edge, we have confirmed its existence from multiple independent directions. We know that the current framework does not reach it, we know that something is beyond it, and we do not yet know what that something is. This is uncomfortable, it is deeply uncomfortable, but it is also, if you allow yourself to feel it fully, something else. It is the most alive the question has ever been, because here is what has actually changed in the course of this journey through the impossible. What has changed is not the existence of the anomalies. They were always there. What has changed is the recognition of the pattern. The individual anomalies existed before anyone noticed they were connected. The double slit result existed before anyone connected it to quantum biology. The dark matter problem existed before anyone connected it to the fine-tuning problem. The hard problem of consciousness existed before anyone connected it to the measurement problem in quantum mechanics. What changes is not the data. What changes is the seeing. The recognition that these are not separate puzzles, that they form a pattern, that the pattern is pointing somewhere, that the impossible is not rare, it is repeating, and that repetition is the most important fact of all, because repetition in science is not noise. Repetition is signal. When something happens once, it might be an accident. When it happens twice, it might be coincidence. When it happens across every domain of science, at every scale of observation, in every era of measurement, with no sign of resolving and every sign of intensifying, it is not an accident, and it is not a coincidence. It is the universe saying something, repeatedly, patiently, with extraordinary precision. It is the universe generating through the operation of its own deepest nature, a pattern of results that the framework used to describe it cannot accommodate, as if the universe itself is trying to show you where the description runs out, where the model ends, where the real begins. The impossible results are not errors, they are directions. Each one is an arrow pointing beyond the edge of what is known. And the arrows, when you step back far enough to see them all at once, are all pointing in the same direction, toward something that has no name yet, toward something that the current vocabulary of physics and biology and neuroscience and philosophy is not yet equipped to describe, toward something that is real and present and generating effects in every domain of science simultaneously, and waiting, with the patience of something that has been here all along, For the moment when the framework that has been failing to describe it is finally, honestly, completely replaced by one that can. Something happened in a laboratory in Geneva that should not have happened, and in a radio telescope in Ohio, and in a superconducting loop cooled to near absolute zero, and in the chlorophyll molecules inside a green bacterium converting sunlight into life, and in the eyes of a migratory bird finding its way across a continent without a map, and in the brain of a patient whose heart had stopped and whose neurons had gone dark, and who nonetheless returned with a description of the room above her body that the nurses confirmed was accurate in every detail, and in the precise values of the fundamental constants that conspire, with a specificity beyond all reasonable chance, to permit the existence of a universe complex enough to ask questions about itself. Something is happening, not once, not twice, not in one domain or one experiment or one fleeting observation. Something is happening everywhere. Something is happening repeatedly. Something is happening with a consistency and a persistence and a precision that refuses every comfortable explanation, survives every attempt at dismissal, and grows clearer, not murkier, but clearer, with every improvement in measurement, every refinement in technique, every new experiment that was designed to finally make it go away. The impossible is not rare. It is a pattern. And the pattern, this is the thing that you now cannot unknow, the thing that will stay with you longer than any individual result. The pattern is not random. It is coherent. It is pointing somewhere. Every impossible result, every anomaly, every signal that should not be there, every correlation that has no mechanism, every consciousness that persists beyond the point where no theory says it should, they are all looked at together from far enough back, with enough patience and enough honesty. They are all the same knock on the same door, and the door has been there the whole time. You just had to hear it enough times to know it was a knock and not an accident. And now you have heard it, and the sound of it does not stop.